Good morning, everybody. Welcome to a special Eclipse SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute.
And I am your co-host, Ryan Lambert. I'm a planetary defense scientist here at the SETI Institute. Thank you, everybody, for joining today. Let us know in the comments where you're viewing from. We're expecting people all over the world. And it's always very nice to see where people are viewing us or watching us from.
Today, we're going to be joined by astronomers from Unistellar with teams on the ground in Oregon, Nevada, Utah, and elsewhere using eVscopes equipped with solar filters to observe the event. Additionally, we will have some special guests on, various scientists, to talk about the science behind eclipses and why solar observations are important.
Yeah, as a reminder, also, this is still the sun we're talking about. So unless you have proper equipment, please don't look directly at the sun, especially during an annular solar eclipse. You will hurt your eyes. Instead, if you have the glasses or you're using a telescope, make sure that you have a proper filter on your telescope, a solar filter.
All right, so let's start by introducing our Unistellar team. Now, keep in mind, they are out in the wilderness areas, and their signals are going to not be so great. It looks like the only one we have right now is Franck, planetary astronomer and chief scientific officer at Unistellar. So welcome in, Franck. Where are you at? Thank you for setting the event up, first off. And then where are you at, and what do you see right now?
So, hey everybody, how are you? So, yeah, I'm in Oregon because I decided that the great challenge for this eclipse will be to the place where we're sure the weather will not be good, but because we wanted to be the first one to see the shadow passing above the US, we decided to go to Oregon. I'm in a place called Art Barn. You can see, I don't know, I have to move slowly because we have a very poor internet connection. It's a very cool, nice place, huge land, and we came here in 2017 to watch the total eclipse, the same place. So that's the reason I really wanted to come here to see this annular eclipse, because
you returned.
Yes, it's a return basically, and the place changed. It's much nicer. It's much better. Willow, who owned the place, been very accommodating us. Look, I'm gonna show you something cool. I had the feeling I'm becoming an influencer here, but that's not the case. But look.
You've always been an influencer, Franck. What do you mean?
Exactly. What are you talking about?
So here you can see yourself in the barn. It's too early in the morning. I'm still having my coffee, so there's almost nobody. But people are gonna come slowly here and watch the show here, hopefully. And hopefully we're gonna see an annular eclipse, a ring of fire. That's the goal. And the eVscope is here, ready to be used. And of course, look who is here.
Stormy, hello, my girl.
Nobody cares about me anymore.
Is she enjoying
Nobody cares about the dog.
Yeah, I mean,
is she enjoying the outdoors?
Oh yes, she thrived in it. She found a bone, I don't know where, so now she's basically keeping the bone, waiting for the eclipse. That's a job.
That sounds like a good job for a dog.
Yeah.
All right. Well, it looks like Lauren's connection is not so great, and apparently Ian has not reached back out to us. So we're going to bring up a view. I'm going to introduce Michael Primm and bring up his view. Hello, Michael.
Good morning, folks. How's everybody doing?
Good. It's early for me. I'm on the West Coast.
Yeah.
Actually,
I should say central time out here in Central Time. So.
Let me say something here, Beth, because I mean I'm very impressed that at 7:30 a.m. you were already awake and ready for this. I mean, kudos, because I know you're a night owl, so you love working late and you hate waking up early. So thank you for doing this.
I was just going to say, I mean, astronomers are not exactly known to be morning people.
No, we're not.
Maybe early morning people.
Yeah, exactly. If I see the sunrise, it's usually from the other side of the night,
Exactly.
right? So yeah, I don't wake up before the sun. I go to bed with the sun. So yeah, it's I'm happy to be here, and this is exciting. So Michael, tell us who you are and where you're at.
Oh, okay. My name is Mike Primm. I'm active member of the Unistellar Citizen Science team. I'm a member of Exoplanet Watch and a couple of other science, citizen science groups. So kind of an active amateur, I guess would be a good way to put it. Professionally computer engineer, mostly doing small startup companies.
Fabulous. Now Michael has wisely found a wired connection and did not travel. So we are privileged to have this wonderful view of the sun from where he is. And it seems fairly stable. The connection seems to be working. So we will try to keep this up as much as possible until we're looking at everybody else's telescopes. So very excited that we worked that out last night.
Well,
Very question, Michael. Will it be perfect? You are part of the centrality, or you further away?
I will be getting, I think it's 88.5% as opposed to 90.12. Okay. So I'm as close to being annular, a proper annular as you can be without actually being there. My choice was either to give you guys a really nice stream here using my gigabit fiber, or to drive out to Fredericksberg this morning and hope for the best.
Right. Yeah. So, good choice. Thank you.
Yeah, well, like I said, I was just like, I just know it's going. You just know the way these things work. As soon as you try to do something a little more ambitious, you know absolutely positively you're going to be regretting it.
Yeah, it's a real reach for the stars situation, and then you just kind of crash and burn. Yeah, the more you put on the line.
Exactly. So anyway, yeah, I've actually got my scope out of my front yard. Hopefully, none of my neighbors will mess with it. And actually, the same screen I have here. One of the things that's really neat with these scopes is I've got my tablet out in the yard, perched next to next to a tree, right next to the scope in the shade. That's showing the same view. So any of the folks that are walking by my yard or so forth can actually get a glimpse as to what's going on here. Which is, I'll tell you, it's one of the things that's really terrific about these scopes is you do community outreach and so forth, and it's a real pleasure.
That's one of the best things, I think. I think that was the main reason, actually, honestly, I got my telescope was, and I don't have an eVscope yet. I know, Franck. But
soon.
But I have a 10-inch job, and taking it to star parties and sharing it with people really is the motivation for getting it, and letting people see some of these astronomical phenomenon with their own eyes is always an amazing thing to do. So thank you for being on here and sharing your tremendous view. At least we are guaranteed one good view of the sun today.
Yeah, well, we'll put a star next to that guarantee and say I might need to scoot out and take 2 or 3 minutes to reposition the scope if we get into some tree intrusion, shall we say?
Not a problem. Absolutely, yeah, that'll be fantastic.
I'll give you guys a warning if that's going to happen. But
cool. All right. So let's see. Ryan, do we want to run a video?
Yeah, absolutely. So
all right. I have it
okay,
set up.
You have it?
So,
sure.
Yeah. Let me.
We're going to show you all, in case you don't have glasses or a telescope with a fancy solar filter, you can still see the eclipse safely by making a pinhole camera, a pinhole projector. So Beth is going to show us a video right now on how to make that. Very cheap, very easy to make, very do-it-yourself, and it's a good way of indirectly seeing the solar eclipse.
I'm Kalisa from the Planetary Society. Today, I'm going to show you a cool and safe way that kids can observe a solar eclipse. All you need is a push pin, 2 paper cards, and a sunny place. We're going to make a pinhole projector. With a pinhole projector, we can watch the shape of the sun change during an eclipse without having to look directly at the sun. To make your projector, use your pin to punch a small hole in the middle of one of the cards. And that's it. You're done. Now take your pinhole projector outside, but don't look at the sun. Instead, look for your shadow. You want to see the shadow of your head and shoulders clearly, either on the ground or on a wall. Next, hold up the card with a hole and rest it on your shoulder so you can see the shadow of the card next to the shadow of your head. Now, hold up the second card until its shadow overlaps the shadow of the first card. Now look at the second card. You should see a small circle on it. The circle is actually an image of the sun. Your pinhole projector has projected it right onto your second card. Right now, the image of the sun on your card is a circular shape, but during a solar eclipse, you'll see a crescent.
Yeah. So incredibly easy to do. Definitely awesome.
Yeah, really, really, really easy to do. It's such a neat way to do it. You can also do some fun things with your hole punches. You can make designs. And you know, I've did it once a few years back when we had the last one. I think in 2012, I made a design where I literally poked like the shape of a heart because I am that girl, and I projected it onto the railing of my balcony because that was the best place that I had a good shot from, and that was really neat. So I had this little, you know, heart-shaped set of solar crescents, which was a pretty cool thing to do. And if you don't have note cards, or you know, you don't have paper that you want to punch holes in or whatever, a colander with the big round holes will work in a pinch. You just do the same thing, project it up on, you know, from through the sun down onto the ground, and you'll be able to see some really cool stuff. You can also use the leaves of trees and that kind of thing. So
yeah, we actually got a comment on YouTube from Alan Gross saying that exact thing. So yeah, even if you're out in the middle of nowhere, you can always make do. Just find a tree and hang out in the shade.
Yeah. What's really neat with the pinhole, once you make it up, I mean, you can use it for eclipses, but if you do a decent job making up the pinhole, you can actually see sunspot groups with it too. So you can use it for more routine stuff as well. I've found when I've made one. So
yeah, that's very cool.
Yeah, it's some, you know, so it's something that you don't have to necessarily wait for an eclipse to use it. So.
Fantastic. Yeah, I'm really excited. So I know I want to welcome.
We just oh, sorry, go ahead. I just want to make sure we explain a bit what the eclipse is before we move forward in the complexity of everything. But go ahead.
No, let me just welcome in some people, and then we'll get into some of the science.
Okay.
Let's see. So we've got people watching because this is a long list. This is going to take a minute. Toronto, and I guess there's some from Windsor. We've got some from British Columbia. Let's see, Germany, Michigan, Quebec, Arizona, Washington, Pennsylvania, New Jersey, South Carolina, Italy, Georgia, England, Idaho, more Canada, Seattle, Dhaka, France, bonjour, more England, Alaska. Okay, cool. New Jersey, Lima, that's awesome. Welcome in from Lima. Massachusetts, Greece, Serbia. Wow, this is all over the place. Lots more from Germany. Some people local enough to hear. Ohio, Mexico, near Roswell. That's a great spot to be, actually. So cool that you're there. I hope that you have a nice dry view. And from what I understand, that was supposed to be a lovely spot. Guatemala, Australia. Oklahoma, North Carolina. I think we're basically like almost at every state now. We have a Unistellar user in the Pocono Mountains. Welcome in, Bob. Sweden. Ooh, okay.
South Africa, Palo Alto.
Just all over Florida.
Shout out to Sophia from San Francisco. That's where I am right now. So howdy, neighbor.
All right. Yeah. So thank you. Welcome in, everybody. This is really great. So thank you for joining us. We're here to try and watch an annular eclipse. For the most part, it'll be pretty partial in a lot of the places. And hopefully the people we have that are in the path of the annularity will actually get to see something. So Franck, tell us what an eclipse is, and what we're looking at.
Okay. An eclipse. What is an eclipse? So an eclipse is an astronomical phenomena. And what happened in this case is that the moon is passing between us on Earth and the sun. So what's going to happen, since the moon has almost the same apparent size than the sun, it will occult partially or completely the disk of the sun. So there is 3 types of eclipse. The most famous one is the total eclipse. That's when the moon is completely hiding the disk of the sun. And in this case, you have full darkness if you are located along the path. We call that the centrality path. It's a narrow band. It can be from a few kilometers to 200 kilometers, 250 kilometers typically. Okay, and in this case, so the moon is it's big enough to hide completely the sun, so you can see the surrounding of the sun during the day. Those are the most impressive ones. Today we are going to see what we call an annular eclipse for the people like me who are on the path. And in this case, the moon is slightly smaller because it's further away, basically, from Earth. So it's not going to hide completely the disk of the sun. You're gonna see a ring still remaining around on the image. That's the remains of the sun disk. We call that the ring of fire. And in this case, the light will drop drastically. I mean, it will be basically like if you're at the beginning at sunset or sunrise. But you still see, you still have light coming from the sun. And then the third one that most people in the US will see is what we call a partial eclipse. So in this case, the moon is not passing exactly, not hiding exactly the disk of the sun, but cropping basically a piece of the disk. So it's gonna be like a Pac-Man. The sun will become like a Pac-Man or something like that. You will see the disk of the moon eating slowly the disk of the sun. You cannot feel those kind of eclipses most of the time. So you need to watch them using a pinhole camera, using a digital telescope, a camera with a filter, or those glasses that I show. I don't know if you have some. Do you have some? I have a few here I can show people.
I have some.
You have some?
I was going to hand them out to my neighbors, and I never saw any of them. So
you don't have neighbors?
I'm jealous.
There we go.
So yeah, those glasses are great. If you don't have them,
look for the
maybe time
solar viewing.
You can also go to the library. Some libraries are still open on a Saturday morning, and grab some, because there is a program from the Moore Foundation and the SETI Institute, so you can get those glasses for free in the public libraries.
And I saw someone in the chat was saying that certain superstores that shall not be named have them for a couple dollars. So if you still need them, you can venture into that Arkansas store, and they have some too.
Good.
I did have a question from the audience, and this is a good time to ask it. Uncle Hairball, great name, is asking, will a welding helmet be enough?
I used that when I was a kid. I stole this to my grandfather to watch my first partial eclipse, and it did work well. So yeah,
I love the idea that your grandfather just had a welding helmet that you could just steal. I was thinking, yeah, sure, it would work, but how are you going to have one lying around?
For that that's the last annular eclipse. We definitely had some pieces of welder's glass, so you could just like hold them up, and yeah, they work fine. So it was, if that's what you have handy, and that is amazing. Yeah, absolutely, you can totally use those. All right.
So I think we're getting a lot of questions about what time, if we want to address that, because that's a particularly tricky question to answer.
It is. And the best thing you can do, honestly, is go to timeanddate.com and follow their links to the annular eclipse, put in your zip code, and it will tell you what kind of path you have and where it will be.
Yeah.
But
So
And
that's
then,
it's hard to say given a particular time because the moon is moving, and because the solar eclipse is so angle dependent, like Franck was saying, it's casting a shadow essentially. So it really depends on where you are. So yes, time and date, absolutely. We can't give you a solid answer without knowing specifically where you are, and maybe don't put that in chat. So yeah, but there are ways to look it up at time and date, like Beth was saying.
so here is gonna start very soon, but we still can see the sun. I mean, I think I remember I calculated it was at 8:35, so we're gonna have to wait for the sun to be shining in the sky if the clouds goes away before doing anything.
so MG Astronomy is asking, I have eclipse glasses that were given to me about 5 years ago. Can these be used? And the simple answer is yes. The more complicated answer is make sure there are no holes, like pinholes or scratches or anything like that on the glasses themselves, on the lenses. And then, yeah, they can absolutely be reused. And then, oh, Miriam is asking, what if a dog looks at the sun during an eclipse? Are you taking any precautions for Stormy there, Franck?
Well, Stormy knows that she should not be looking at the sun. She has this natural instinct that make her not want to look at the sun. That's kind of that's the way evolution worked. In fact, the animals who decided that they could watch the sun, they die before growing up. So so the one remaining are the one that knows that they should not watch the sun directly. So Stormy is part of the survivor in the evolution chain, and she knows that she's not going to look at the sun directly. It's early in the morning for me. I'm sorry.
No.
I think Ryan and I feel that too. We're all here with you. So.
Yeah. And honestly, it's not like that's a good question and a good answer, because it is something where you can't control what a pet's going to do. But in general, pets not going to look at the sun, whether or not there's a solar eclipse happening.
All right. Let's see. So I did see. Okay. So Jean Bozeman asked us to quickly explain how to make a pinhole camera, and we did that. We ran a little bit of a video. I will actually put that link in the chat for people. So if you need to really quickly see how to make a pinhole camera, this is how to do it. Thank you, Planetary Society, for this really excellent little short video. And I just realized that Jean was asking from LinkedIn, so let me go paste that over there because it doesn't go directly. And yeah, and the other thing that you can do, as we talked about, you can also just really simply take a colander, or punch a hole in a piece of paper, use it, and just hold it up over your shoulder and project onto the ground so that you're not actually looking at the sun. So just check which way your shadows are going. And also you can use the leaves of trees. The shadows between them will also show you where those crescents are. So it's a really good way to kind of look. All right. We are now at 8:30. And I think we can check in with Dave. So Franck, I'm going to let you go for a minute. I know you need to put your Wi-Fi extender in. So
Yep.
Go do the thing, and we'll see you back here in a few.
Yep.
Okay, thank you. I'll be back.
All right, let's check in with Dave. Hey, Dave, can you hear us?
I can.
Fantastic.
How do you hear me?
We hear you fine. There's a little bit of wind, but it sounds good. So tell everybody who you are and where you're coming from.
Well, I'm Dave Coster. I am standing on a beautiful hillside near the East Library of the Pikes Peak Library District, and underway, if you can see, underway in front of me is the party. So the library district invited everyone in the Springs to come and enjoy this. And right now we have many of the people that attended our lecture yesterday. We had 120 people that we lectured and described how to see the eclipse and the physics behind it.
Looks like you have some really good skies too.
They're high cirrus but not interfering at all with the view of the sun.
Oh, fantastic.
And in the background there is Pikes Peak.
Oh, very nice.
That just makes me homesick. I was born beneath that mountain.
It's a wonderful spot. And if I have to air gap the view of the sun, but I'm going to do something here. There we go.
Oh,
So
yeah, you
that's
can
the-
even
Ooh, very nice.
you can see it starting.
Oh wow, look at it
Yep.
starting.
Yeah, we're probably about 10 or 15% right now. We have maximum, of course, at 1036, and it's going to be about 81% here.
Oh, that's fantastic. What a great view is, and that's the view from your eVscope?
Yes, yeah, I'm sending that to my phone. The Wi-Fi here is pretty bad, but I'm sending that to my phone so I can use the iPad to show the view.
Oh, that's fantastic. Have you got a lot of people coming over and checking in on you, or are they wandering all over the place?
Yeah, no, they're coming and checking in droves, but unfortunately, I've got you in my ear, and so I'm very distracted. I haven't been able to give people much attention. I'm carrying on two conversations at once, trying to monitor the scope. So that's where we are right now. Thanks for
looks
letting
like
us join you.
Yeah, absolutely. And Dave,
absolutely.
thanks for showing us that. Much appreciated. We will let you get back to talking to the people that are actually around you, and
Thank you.
and focus on that, because this was great. So thank you for being here, and enjoy the view.
Thank you.
Thank you. All right. I don't want to be in the solo view. Let's bring everybody back on.
Oh, yeah, we could see it. So this setup right here is another citizen scientist, Michael Primm. We can see as well that the moon is starting to peek over in his eVscope as well.
Yeah, look at, you can just see it cutting in at the top there. So that's fantastic. And I know Michael's in the stream with us. He's just not on camera at the moment, and that's fine. But we can definitely see.
You could see that I was busy tinkering.
Yeah, just fine.
Sorry, just had to dash back out there. I'm like, okay, when I saw that much coming in from the other view, I'm like, okay, it's just off the top. Let me see if I can fix this.
But you could see it cutting in, so that's really good. And you can also see sunspots there. Ryan, what are sunspots?
So sunspots are areas on the surface of the sun that are colder than the rest of the sun, but not by much. So maybe 1,000 degrees colder. They're around 5,000 Kelvin, I think, if I remember right. So one of the interesting things about the sun is that it's so big and its magnetic field is kind of weird. It gets shifted around as the sun rotates. The magnetic field kind of gets dragged along with the sun, and it gets twisted up. And as the sun continues to rotate, that magnetic field gets so twisted up that it starts to kind of it's almost like a water hose. When you've twisted it around, it kind of kinks up, and so that magnetic field ends up jumping out of the surface of the sun and then back in, and that keeps the material that's on the top of the sun from actually sinking back down. So normally we think of hot stuff, hot air rises, cold air sinks. It's the same with the sun, but the magnetic field is keeping that material in place. So when it's cooled down, it's not actually able to fall back down. That's why a lot of sunspots will come in pairs.
And so we're definitely seeing a couple good spots over there, as well as the cutout of the moon starting to peek in here.
Yeah. So the sun has a sunspot cycle. And if I remember right, we're heading towards the maximum at the moment. Mm-hmm. So within the next few years, we'll see more and more sunspots gradually appear on the surface. And eventually what happens is the magnetic field just kind of breaks and then starts again, resets itself.
Oh, right. And so when they break, that's actually kind of an important thing to know. So what happens when your magnetic fields on the sun twist enough that they break, and what do we get from that?
So you can get coronal mass ejections. There is flares. There's basically lots of the solar activity that sci-fi shows will like to talk about. Of like we're getting a giant flare, we're getting a giant coronal mass ejection. That is a consequence of magnetic field breaking. It happens outside of that as well, but the magnetic field breaking is usually a pretty big event. Not enough that we would ever notice without having special telescopes or without having special equipment. So we're not in any danger. But yeah, it is when it ends up breaking, and then it just resets itself with north and south switched. So it's very interesting. A full sunspot cycle is actually around 22 years, if I remember right, because it has to go again, so that the magnetic field goes north and south, and then it breaks, and then south and north, and then it has to go again to reset itself back to the beginning.
And so it can be a very these coronal flares and coronal mass ejections can affect Earth pretty severely if they're bad. We had the Carrington event, which actually took out telegraph capability for a while. It actually knocked out the telegraph wires. They basically just fritzed.
Caught fire. Yeah, some of them actually caught fire. So there is. I wanted to downplay a little bit because I don't want people to just live in fear of the sun. But yeah, if we're really unlucky, they can really affect our electronics. But they also cause the aurora. The auroras that you see in the northern latitudes, southern latitudes, they are caused by charged particles entering the Earth's magnetic field, and they end up fluorescing the atmosphere. So some beauty that comes with it, as well as the risk. That is a thing about living here in the San Francisco Bay Area that is sort of frustrating, is that like I'm not going to see the aurora from here, and if I am, I really probably didn't want to. Yeah, that's maybe not a great thing.
Yeah, exactly. I mean, I have family in Minnesota, and they're always like, "Hey, let us know when there's the possibility of a flare," and it's like, okay. I kind of dislike all of you right now, so.
The auroras are amazing, absolutely amazing to see. I had the good fortune of being on a cruise ship going across the North Atlantic, so I was basically between Iceland and Greenland, but middle of the ocean when there was an event, and it was breathtaking. It was amazing to see.
Oh, look at that cutout coming in. That looks so good. And Michael, you said that you're gonna get about 88%.
Yeah, it should be just as close to being an annular as you can be and not be. Okay, that's basically if the closest point where you get the maximum coverage is about an hour west of here.
Wow. Okay.
Yeah. Although unfortunately, part of why I traded off on going here was the weather forecast was getting a little dodgy out that way. They were getting concerned that there was going to be some clouds coming in from the west, and so we'll, best of luck, because I know at least one person who actually flew to San Antonio, and is out there right now with trying to observe it. So I'm hoping for the best for them.
Mm-hmm. Yeah, that's actually part of the struggle for this is because this is an event that's covering such a wide area. We wanted to make sure that everyone was in the path to see it. There's weather in all the different areas where people are set up. So we've had a few people that we had planned to check in with that they ended up telling us this morning or yesterday, like, the weather forecast isn't good. I'm not going to be able to see it. So it's been tough to plan. It's always a challenge for these kinds of events that cover such large distances. Well, so I'm glad that you have the weather, even if it's not the full annularity. It's close enough, I think.
Well, I know actually. I mean, going back to when I was a kid, it was one of the there was a totality that we could see from up in New York where I grew up, and didn't see a darn thing because of, had cloud cover, so it got dark.
Yeah,
and that was my last chance that I've actually had anywhere around where I've lived until, well, at least until this spring, because actually my home is actually in the path of totality for this spring's event, so I'm really
that's awesome.
looking forward to that. So
yeah, so for those in chat who maybe don't know, there is also another solar eclipse that is going to happen in April of 2024. So if you missed this one, or you realize, you didn't know it was happening, there's your shout out. There's the next one coming. And that one's going to be a total solar eclipse, which not knocking annular solar eclipses. They're very cool. It's super neat to see the ring of fire, but a total solar eclipse, sky goes dark. It's a very surreal experience. Absolutely worth traveling to see that if you can.
Yeah, it's really amazing. There was one that actually went by my house when I was in high school, and that was really, really neat to just be able to go outside and watch this happen. So there are people that chase eclipses that will go all over the world to capture them. There are tourist companies that are basically they put together eclipse trips. But I will tell you that if you're now excited about it from watching this happen, a lot of hotels are already booked. I tried. We were going to go to Nova Scotia and then go where my husband is from and stay with his family, and then head over to New Brunswick or PEI, which are both in the path of totality, and the hotels are just
It's an event that because they're so far known in advance, and people really jump on that, you've got to be prepared, or you've got to be willing to do what I did and sit in a park 2 states away and accept that there's going to be an 8-hour drive back home.
Yeah, that's, well, I know and you got to figure if you're going to go like spend the money and plan months, weeks, years ahead of time. The weather's the weather. Yep. Wherever you're going to be, the weather's either going to be good or bad there. Okay. so yeah, it's definitely, well, that seems like something that'd be, I don't know. Once you're retired, it seems like it could be something that would be that much more interesting to pursue.
Oh yeah. I mean, if I had the money, I would absolutely chase eclipses. I think that would be so cool to do. But I do not have that kind of money.
No, I've had some colleagues who've done it on like cruises or there was one where I know someone who went down to Mexico and they had like this really nice resort that they stayed at, and it was just a bunch of astronomers all out watching the eclipse. And I'm very envious. I would love to have that kind of money, but I just hope it comes here sometimes.
Well, you also have to look at it this way. If you're going to travel across the world to go catch an eclipse and you go to a beautiful resort to do it, no matter what happens, you're still at a beautiful resort.
It's true, which is probably good because I have one specific friend who is known for bringing clouds. Do not go try to watch an eclipse. Do not. We were at a big Star Party event in Southern California, high desert. The humidity is like 4%, and by the second night it had started to cloud up, and so like the last 2 nights of it we had no visibility, and we were just like, how do you do this? so figure out who those friends are and do not go with them.
I'm sorry. I hope this doesn't affect our friendship, but you're not coming.
A few people in the chat know who I'm talking about. Yeah. This is a known terrible superpower that she has.
Wow.
So we do have a chat from a question a little while ago from Damon Dawn asking if there are other planets that have eclipses like Earth. And I just wanted to get to that because, yeah, absolutely. If you have a moon and it's orbiting a solar system body, that there will be eclipses on that body. whether they are annular like this, where the moon doesn't fully cover the sun, or whether they're total solar eclipses. Doesn't matter. Those still count. So all of the solar system bodies that have moons will have eclipses on their surface.
Well, actually, one thing that's really exciting to think about it, several of the things that we actually do in the citizen science world, where we use our telescopes to help contribute to the astronomical observations, are in effect eclipses, observing eclipses. For example, if you're watching transiting exoplanets, ultimately what you're doing is you're watching the effect of a planet around another star, crossing in front of that star and making it become a little dimmer and a little brighter, and observing the planet that way. Or we also do asteroid occultations. And if you really get down to it, an asteroid occultation is an eclipse of some other star by an asteroid in our solar system.
Yeah, so I didn't know that was possible until I started.
No, it's remarkable. It really is.
Yeah, you can see the shadow that an asteroid casts as it passes in front of a star. We can see that on Earth is amazing to me. So yeah, I love that about the eVscope as well. I think that's very cool.
What I found remarkable was learning how much scientific value there was in doing that, right? The fact that the most accurate way we can track the position and shape of an asteroid can be by tracking the shape of the shadow as from a star as it passes across the Earth. You wouldn't think this, but that's actually the case. And once again, you can do that as an amateur astronomer, which is a blast.
Yeah, and that's I personally love occultations, because even when you miss, you feel like you've still contributed, because not knowing where the asteroid is or knowing where the asteroid isn't is just as important as knowing where the asteroid.
Well, and it makes the hits that much more sweet, right? Okay, because the fact is, like I said, we don't know exactly where that asteroid is, and part of what we're trying to do is figure it out. And depending on exactly where that shadow goes, you might get a hit, you might get a miss, but when you do get a hit, like I said, it's a little something to celebrate. It's a lot of fun.
Yeah, I think my favorites are where you get that hit, but it's just a touch. Like you got the very edge of the asteroid, so you know exactly where that asteroid is ending. So that's if you get a lot of, for people in chat, we were talking about the shapes. The idea behind this is that you have lots of people set up a few kilometers apart. And they're all observing this one star, and the star, depending on where you are on Earth, will wink out as the asteroid passes in front of it. So you'll have all of these different images of the star, and you can figure out, okay, the star from this one position, the star stopped being visible here and started being visible here again. So we know that the asteroid is moving at this rate. It has to be at least this long. At this point. And if you get enough people together, you can actually trace out this idea of what the asteroid kind of looks like based on how long the star goes missing for each person that was observing. So if you get that very edge where this, like, it just blips for a second and then you come back, you've got the edge, you've got the very end of that asteroid.
Yep. No, that's like I said. It's like I said, before I got into it, I never would have guessed that these different forms of eclipses could be of such besides being fascinating to observe, also could be so useful for actual legitimate science. Not simply like, ooh, that's kind of cool. That sort of thing is great, but actually doing these things and saying, wow, this is, well, because I'm here, I may be a little telescope or so forth, but like you're saying, the gang of us doing an observation and being able to, you're kind of creating little scan lines across just imagine you got the shadow going across the Earth, and where you are, you're measuring the length of the shadow as it passes over you, and you add that up with the people a few miles to the west or a few miles to the east or so forth, and you can derive the shape of the rock, which is, once again, it's remarkable, particularly in, I think, once again, how innovative astronomers are at finding ways to pull information out of observations like this, out of data like this. You know, the ultimate challenge of being observational science as opposed to experimental science is learning how to make the most of your data any way you can get it.
Absolutely.
All right. Well, that was a lot and really cool information. And if you want to participate in citizen science, Unistellar has opportunities. So, observing asteroid occultations is one of them. We're going to welcome in a guest, Aparna. I'm just waiting for her to turn her camera and mic back on. Here she comes. Michael, I'm gonna let you go for just a minute.
Mm-hmm.
Hello, Aparna. Welcome in.
Hi, good morning.
Good morning. Aparna is a postdoc at the Bay Area Environmental Research Institute, whose doctoral research involves space weather predictions, which is when we talk about, having eclipses and things like that, or not eclipses, aurora. Mm-hmm. She's currently doing research on coronal heating in active regions of the sun, and she's here to talk about some solar science with us. Welcome in. Thank you for joining us this morning.
Yeah, thank you for having me.
It's a little bit early for you too, right?
Yeah, it's early. I had another meeting earlier, like at 7:00. But
oh no,
so I'm up since a while.
Wow. So tell us a little bit about yourself and what your research is.
So currently what I'm doing is looking at like just how you're able to see sunspots on the sun right now. I'm looking at sunspot regions and active regions, mainly not the quiet parts of the sun. I'm sure that is also pretty interesting, but right now I'm just focused on the active regions. I'm trying to study how the heating occurs in active region loops. So if you see in extreme ultraviolet or X-ray images of these active regions, they appear like really bright, and they are bright because they are also hot. And so I'm basically trying to understand how this heating is occurring and why they are that hot or why they are bright and stuff like that. So basically, there are like a couple of theories that explain why this heating might be going on. Like one of them is the nanoflare heating theory, and the other is the waves. So with waves, it's like there is the convection zone with like a lot of plasma or like the gas in the sun. The sun is a big ball of gas, right? So this gas is like heating up, coming up onto the surface, and then it cools down, goes back down, and then that repeats. So it's similar to like ripples forming on like a pond or something when you kind of disturb it. So this convection of the gas in the sun is causing these ripples and basically generating these waves. And the waves some of the waves are strong enough to like travel up in the atmosphere and kind of dissipate there and heat the corona. So this coronal heating is a big problem in solar physics. Like we kind of don't understand exactly what is happening, but these are the leading theories. So the dissipation of the waves heating the corona, and then the other one is the nanoflare heating, which is mainly like reconnection between opposite magnetic field lines. So the sun is all about magnetic fields, and there is like these active regions which are strong magnetic fields, right? So these within the loops, they at least if you've looked at the images from Solar Dynamics Observatory of the full disk of the sun, it looks like a band of like bright loop. But inside that loop, there are these like smaller, small scales and smaller lines of magnetic field lines, which are like probably trying to reconnect with each other and then cause small scale heating events, which just dissipate over there and cause the local heating. So this reconnection is very similar to what causes solar flares, but solar flares are really explosive and it releases a lot of energy, which enough energy to affect us here at Earth, right? But these nanoflare heating are like nano, and they're like smaller scales and smaller energetics, but they're enough. They're probably enough to cause heating on a smaller scale as well.
Interesting.
So those are the leading theories, and what I'm working on currently is mainly related to the nanoflare heating. Yeah.
Oh, that's very cool.
Thank you.
So how did you get into this? Were you researching this? So I know you just started your postdoc. Was this your research before as well, or did you kind of fall into this?
Yeah, I think I kind of fell into this. My PhD was on space weather predictions. So I think it's just like using different kinds of data. And then I had worked a little bit on this subject before I started my PhD for a while in India. Yeah, it kind of led into this. But yeah, I'm glad because it's a different topic to explore and kind of understand in depth. So it's kind of cool.
Absolutely.
So for your current research, I know earlier in the summer, I think there was they were teaming up the Parker Solar Orbiter or Parker Solar Probe and the Solar Orbiter to figure out to work on this coronal heating problem. And have you been able to work on that specifically?
No, right now I'm just using data from SDO, the Solar Dynamics Observatory, and also from IRIS a little bit. But yeah, I haven't had a chance to look at PSP and Solar Orbiter. That would be cool.
Yeah, I guess they were teaming them up so that they could do kind of combined observations and get two different views. And if you haven't, I'll share the story in the link. Because you guys, they had to basically like shift things around a little bit, I think, for the Parker Solar Probe in order to make it work. And so they were basically having to like time these two observations at once. And it's an amazing bit of science. And hopefully, Aparna, you will get to see some of that data, because I understand that it's actually specifically for this particular problem.
Yeah, that would be cool. I agree. Like they're both going close to the sun, and I think they're at different points in the orbit. And yeah, it is kind of a challenge to like point them at the same thing. And yeah, that would be cool to get some of this data.
Let's see. Well, so if there are any questions in chat as well, I'm wondering if looking to see if there's anything in particular that we might be able to ask you from what people in chat have.
Well, so Beth is asking, this might be a good one. When the sun, the moon, and Earth align in a straight line, are there any effects on Earth's gravity or on our magnetic fields?
So, is that something that you would know? I think we could probably all answer this a little bit. But yeah, if you want to take a stab at that, Aparna.
Yeah, sure. I mean, of course, it causes effects on like the tidal effects and like the oceans, causing high tides and low tides, and whenever the moon is aligned with the sun. But with respect to magnetic fields, I don't think there is much that it can do. Yeah, you can go ahead and answer.
No, I think that was pretty much what I was going to say, is that gravitationally, you would see a small effect, tides for sure. But magnetic fields, I don't think the magnetic fields reach far enough out on Earth or the sun. I just don't think there's really any effect during an eclipse. It's more of just an interesting geometry of the three bodies than it is something that will cause effects.
The mainly magnetic fields are affected by what is coming from the sun, mainly like the coronal mass ejections or the solar flares, because the coronal mass ejection is also like a big magnetic body, although it doesn't it contains mass, but not as much as to see. Like we can't see it with our own eyes or something, but it does affect the magnetosphere. Like if it comes close to the Earth, it can do the same thing as reconnection, or like cancel out the magnetic fields and then cause like a geomagnetic storm or something like that. So I think that would be an effect on the magnetic, like the magnetic field of the Earth, but not just the alignment of the Moon and Earth with respect to the Sun.
Mm-hmm. Yeah. And
So,
go ahead.
No, go ahead, Ryan. Go ahead, Ryan.
Well, I was just gonna, I guess, address a comment. So I have said in this stream an annular solar eclipse. What I mean is an annular solar, or I said an annular eclipse. I mean an annular solar eclipse. Mike has already addressed that, I think, on YouTube. But yeah, when I'm saying annular eclipse, I really mean annular solar. So the sun is being blocked by the moon. Just so there's no confusion from the people watching.
So this is happening. This is streaming from Oregon right now. Is that?
This one is actually streaming from Texas. Here, I'll bring Michael.
Right. Okay.
This is from his.
Yeah.
Okay. Yeah, I guess it's
fortunately the weather's holding here
in the East Coast.
Yes. So we are waiting for Franck to get set back up. When he is at the time of the total annularity, we'll move back over to his view, and he's set in Oregon right now. But I believe he told me he's getting breakfast at the moment. So he's getting breakfast before his time to shine.
Well, it looks like we've been joined by Homera Herrera, who I don't believe. Oh yeah, no, you are on our schedule and you will be here. Let me bring you in, Michael. I'm gonna just. Hello, Homera. How are you doing?
Good. Thank you for having me. I was just getting familiar with the app.
Oh, fantastic. So I know you're going to be back on later to kind of look from things. You're down in, are you in Florida or where are you at?
That's correct. I'm in Tampa, Florida.
Okay. Fantastic. Well, we will have you back on in a bit. We're going to get back to Aparna, but thank you for joining us, and we'll see you again in a few.
Okay. Bye-bye.
All right. So Aparna, why are we studying solar eclipses?
That's an interesting question. So from the ground, when you see, at least in a total solar eclipse, you can see the corona, which is which is this wispy, very faint region of the sun, but it's like really hot, but it's very low dense. That's why it's very wispy when you look at it during a solar eclipse. And even the slightest amount of disk can overpower the light coming from the corona, right? So it can only be studied from during a total solar eclipse. And it's important, it's useful to study the corona like that because you can get like the magnetic field orientations in the corona, which is kind of not possible. I mean, or we don't have the instrumentation capability yet to get from like the extreme ultraviolet images or X-ray images and things like that. So using ground-based like visible or IR infrared, we can get like polarization information when you look at when you point your instruments at the corona during a total solar eclipse. And this is what they do even when they want to get this kind of information from space-based observatories. Like they observe specific wavelengths that are like specific to the corona and then kind of block the disk of the sun using artificial coronagraphs and things like that. But during an annular solar eclipse, that the corona is not visible, so this type of studies cannot be done. But of course, there are a lot of studies I was reading that related to how the atmospheric changes occur during the solar eclipse, and like these helium balloon experiments to study the ionosphere and things like that. That's pretty cool. Like that would be interesting to learn about.
Fantastic. So we've talked a little bit, we've mentioned a few different missions. Can you kind of elaborate on what SDO is and what it's being used for?
Yeah, so SDO is Solar Dynamics Observatory. It has Atmospheric Imaging Assembly, AIA, and HMI, which is the Helios, I forget, but it is the magnetogram imager or something like that. So I'm forgetting right now, but it gives the magnetograms from the photosphere. So it essentially gives you the magnetic field active, like how strong the magnetic fields are in active regions, and like the different components like the VX, BY, BZ, and things like that. And then the AIA, Atmospheric Imaging Assembly, it basically observes the one wavelength in the chromosphere, and then a few wavelengths in the corona, corresponding to the corona. So it's mainly to understand the dynamics of the corona, and also what is happening in the upper chromosphere. And there is also one wavelength which is very similar to what is being telecasted right now. So it shows the disk of the sun, like how we would be seeing it. And you would see this yellow color, and then the sunspots and everything. And in the coronal wavelengths, you see mainly like these coronal loops wherever they are hot, which means that they are hot in extreme ultraviolet or X-ray. It doesn't go on to as much as X-ray, but like a long range of extreme ultraviolet it studies. And so there's a lot of science that's come out of the SDO mission, including some aspects related to coronal heating, studying the waves in the like traveling in the atmosphere, and these prominent structures which are part of the coronal mass ejections, right? So and you can observe them using the using AIA images. And just the dynamics of how how the reconnection is happening, or how these eruptions are occurring, and what are the different dynamics that are happening during this time, which enable us to understand the physics. And also it helps like do the forecasting before these events occur, like to understand how, if it will affect our Earth or not, such things.
And the other two that we talked about a bit were the Parker Solar Probe and the Solar Orbiter. Can you talk about a little bit about what each of those is sort of doing? Obviously they're getting close to the sun, closer than we've ever been before. But what are those two missions working on?
Yeah, so the main questions that most of the missions want to answer is about how the energy transportation occurs from the surface of the sun into the corona, and how the corona is basically heated. And also there is this question about how the solar wind is what is the origin of the solar wind, like where does it start on the sun, and how it is accelerated, because these are like they go miles or millions of kilometers into the solar system, right? So what is the process that accelerates it, and what is the origin? So I think these are the main things that PSP and a solar orbiter would like to understand. And then there is also like the structure and dynamics of like the plasma, and the associated like the magnetic field that are the sources of these, like the solar wind, and the processes involved in that.
That's very cool. So yeah, I'm not sure. I guess Beth is probably getting water or something. But yeah, that's very neat. Thank you for sharing that with us. Just so that everybody who has joined in, because we haven't repeated it in a while. So thank you all for coming, everybody watching. We are currently talking with Aparna, who is a postdoc at, sorry, I've got to relook at bios real quick. The Bay Area Environmental Research Institute. Yes. And we are currently live streaming the annular solar eclipse from different areas around the United States. So thank you all for joining. Let's see. Trying to make sure that we have hit everything that we need it to. You can see here the moon has really moved in the past 10 minutes. It's really covering a lot of the sun now. So that is, you're getting a live view of one of our users, citizen scientist Mike Primm, his eVscope. The Unistellar eVscope is a digital telescope that he is live streaming to us right now. His view of the sun outside of his home in Austin, Texas.
Mm-hmm. Yeah, I'll tell you what's really great is that being able to see the sunspots also makes it a little easier to track the movement as things are moving across there. Gives you a little bit of a frame of reference. So it's been fun watching this. I'm in here and I'm just kind of hoping that none of my neighbors mess with the scope while it's out in my front yard. Well, I tried to placate them by setting up my tablet next to the scope, which has the same view that you folks have on there, so anybody who's walking by can actually see what's going on instead of trying to blind themselves. So, but,
well, let me thank Aparna for being here.
Yeah.
Aparna, thank you so much for coming and talking to us about
thank
solar
you so
science.
much for this opportunity, and thank you for having me.
Yeah, absolutely. It was fantastic. Good luck with your research, and let us know when you've got some papers coming out, and we'll have you back on for a SETI Live.
Absolutely.
Thank you so much. Thank you.
All right, thank you. All right. Let's see. I think we want to check in. I'm going to see if Lauren is.
Looks like she is getting set up.
Can you hear us, Lauren? Are you slightly available yet? I know she was changing locations.
Can you hear me?
Yeah, there you are.
Yeah, I'm holding my phone up because it's my
we can see that.
It's my source. Yeah. I'm actually out here at Snow College in Richfield, Utah. They are having like a really, really cool festival. I'm not sure if you can see. I'm going to try to point my my telescope screen. There's weather, or my telescope screen, my computer screen. There's actually weather balloons. There's balloons that everybody is sending up for observations. I'm not sure if you can see any of this. Hi.
It's hard to see the.
Yeah.
Oh, are they still like down on the ground? Is that
the?
Yeah, they just sent some up.
Okay.
And there's a whole slew of people. There's probably thousands of people out here that are observing the eclipse, which is really lovely. So I think I'm connected.
And now she is a robot.
She's auto-tuned.
I mean, this is the live
Can you hear me
streams,
now?
people.
Yes.
Yeah, now we can hear you.
The phone has to go back
up. Yeah, the phone's got. My arm is just going to be numb. By the end of this, I may lose feeling. But yeah, I'm still getting my telescope set up right now to observe annularity. But I think I'm here. I think I'm here for the long haul. So, Mike, thank you for sharing your screen. It looks great. And I'm still getting set up, and hopefully we'll all be able to see that ring of fire.
Excellent.
Lauren, do you know what the percentage is that you're going to have there? Are you going to have complete annularity?
Yes, I'm in the path. So I have Richfield is really, really, really close to the very center of the path. So annularity for me should last about 4.5 minutes. So for those who don't know, the closer you are to the center of the path, the longer annularity is going to last for you. So 4.5 minutes is about the longest that it will last for anybody in the path, and that's the time that I have to make this happen. And annularity for me start in about 15 to 20 minutes. So yeah, this has been an adventure so far, but it's absolutely gorgeous out here. It's amazing to see so many families, so many kids, just everybody traveling from around the US and even around the world to see this. It's really fantastic.
Well, you are an amazing Statue of Liberty, and we're gonna
trying.
come back to you in a bit
Yes.
and let you rest your arm for a little while. And I think what we'll do is we'll bring. It sounds like if your annularity is going to be in about 15 to 20 minutes, let's go ahead and bring Lucianne on early. That's me warning her in the backstage area, and we'll talk to her in the meantime, and we'll come back to you. So go rest your arm. And
Awesome.
we'll see you in a little bit.
Thanks, I'll see you in a bit. Bye.
Okay, bye. All right. Joining us next is astrobiologist and chair of the SETI Institute Science Advisory Board, Lucianne Walkowicz. Thank you for coming. Their astronomical research seeks to understand where and how we might discover alien life in the universe and how stars influence a planet's suitability for life. So welcome, Lucianne, and thank you for being here today.
Thank you. It's great to be here. It's raining very hard in Chicago, so I am excited to be able to see the sun, at least via my computer.
Oh, well, that's, kind of, oh, wow. Okay. The clouds have broken up here, and I'm sorry. This is kind of amazing. I don't know if you guys will be able to see this, but there's a tree outside my window. I don't know if I'm going to be able to show you. Let me pull this up as solo layout. And I don't know if you could see it, but the shadows are actually crescents on this tree outside.
Oh, wow.
So it's unfortunately it's just too bright. But let me try this one. Alexa, turn off computer. I can kind of see it, but it's still really bright out there.
Mm-hmm.
But
Maybe for people watching at home, it would probably be really helpful to hear an explanation of how that works.
Yeah, absolutely. Let me get myself out of solo layout. So yeah, that's so basically it's we were talking about this earlier with the pinhole cameras. So Ryan, can you talk about the pinhole cameras while I fix my own camera?
So I actually don't know a whole lot. I feel bad. I'm a bit of a failure on that front. I do know that there is the light essentially is coming in a straight line. But in terms of actually the mechanics of the pinhole camera, I feel very bad. I have forgotten a lot. I know I learned that in undergrad.
Well, I mean, for people who have never seen this effect that a tree creates,
Mhm.
it would probably be helpful just to know it, first of all, that a tree's leaves, when, we don't think of like a tree being a pinhole camera, but when you have that overlap of all those leaves together, right, you get these little spaces act like pinhole cameras. And so earlier when we're talking about pinhole cameras, like the cool thing about them, right, is that it takes sunlight and projects onto, if you're making one at home, and you can like Google how to do that if you haven't seen it on the broadcast today, but you can project an image of the sun. And so what trees do during solar eclipses is they basically make natural pinhole cameras, just because you have like little points, like the leaves are overlapping enough that you have like many tiny natural pinhole cameras. So if you have, like a house nearby or like a smooth piece of sidewalk or something like that, if you're anywhere in the eclipse path today, you should be able to see a projection safely without looking at the sun.
Yes, and I think we did mention that earlier, but it is good to reiterate that because some people have come in since the beginning of the stream. That is even if you don't have a way of like punching out a piece of paper, if you're in the middle of nowhere, the trees are a great way to kind of do it yourself without having to do it yourself.
Yeah. So I'm gonna see if I can. I'm gonna step away in a few minutes and see if I can get a good picture of these crescents, because they're absolutely stunning. So Lucianne, we brought you in here to talk to us about the sun, life, and habitability. So let's start with the sun. What do you study about the sun, and what's the work that you're doing right now?
Well, so my expertise is in the magnetic fields of stars. And so a lot of the things we know about the way that magnetic fields work in stars is entirely from the sun. I think it's something that people maybe don't appreciate just because you don't have to think about it, is that the sun is really the star that gives us everything we know about other stars. when we look at the sun, for example, like our ability to see the solar surface and these wonderful images that we're receiving from people in the eclipse path, all of that is, for the most part, impossible with other stars. We don't have any other star in which we can see this like beautiful detailed surface. You can't send spacecraft to other stars, at least at the moment. And so, the sun is really the place that we study all of these phenomena that affect the planet, much in the same way that the Earth is the planet that teaches us about life in the universe, because it's the one place that we have an example of life having originated and evolved over these past several billion years. So, when we look at the sun as a star, a lot of the things that we can't study in other stars, we can study in detail in the sun. So there's this wonderful, like, cooperative relationship between the things that we can learn about stars and the sun itself. So, I guess in that sense, the sun has been like one of my greatest teachers in trying to understand how stars affect whether planets can have life on them or not.
Yeah, I think that's an excellent point. That even for astronomers, you kind of take it for granted that the sun is the closest star, and that it is up by itself excellent probe for what the rest of the universe is like, for what other stars are doing, because we can actually study it much better than anything else out there. So yeah, that's a great point. About how useful the sun is, just in terms of studying and then using that as a correlation for the rest other stars out there in the galaxy.
Yeah, and I think one of the sort of confounding things about being a person who thinks a lot about the search for life in the universe is that not to diss the sun on its special day, but the sun is not the most common kind of star in the universe. That honor belongs to a kind of star called red dwarfs or M dwarfs that are half the size of the sun or even smaller. And with those stars, so when we talk about like whether a planet could be what we call habitable, able to support life, a lot of times, that's, in fact, all the time pretty much, it's based on our observation of our own solar system. So here on planet Earth, we are at a distance away from our star where we get enough light that we're the right temperatures. So some people call this the Goldilocks zone or the habitable zone. We're not too hot, so we're not too close, and we're not too cold, we're not too far away. So it's a little like thinking about it like a campfire or something, where you want to be the right distance, that you're getting the right amount of heat, not too much, not too little. Now, with most of the stars in the universe, those stars are kind of like campfires that are only glowing embers, right? They're not burning very brightly. They live for long periods of time, but they just don't put out a lot of energy. And so the planets that would be in their habitable zones, in order to get like overall the right amount of light, would be very, very close to those stars. And so one of the important things is that when we study the sun's magnetic field, we can see certain aspects of the way that it affects life here on Earth. So, one of the more beautiful ways being the aurora, right? When we have charged particles coming off of the sun that hit the Earth's magnetic field, cause our atmosphere to fluoresce in all those beautiful colors that, if you haven't had a chance to see them live, you've probably seen pictures of them. If you haven't seen pictures of them, you should go Google them right now because they're beautiful. But we can observe that. We can see the ways in which flares, not only the energy from flares, but the material that comes off of the sun, these so-called coronal mass ejections, impacts our atmosphere, affects atmospheric chemistry here. All of that having implications for life on this planet. So then, when we try to extend that knowledge out to what we might want to learn about these planets around little red stars, where the planet has to be super nestled up against its star, that means all that magnetic activity that star is also doing, and that is sort of analogous to what's happening in the sun, is going to be like, you have front row seats. So we expect that magnetic activity is going to be a much bigger effect for the planets. And it's been a really long period of time in which people have debated whether those planets could host life or not for that reason.
That's interesting. So I guess, is the idea of the magnetic activity for red dwarfs, do you expect that is analogous to what we see in the sun, or is that still up for debate on exactly what kind of activity is happening for these red dwarfs?
Yeah, so one of the things that I think makes astronomy so amazing is, and this is sort of like a profound truth about the universe, is that physics and chemistry work the same everywhere, and that's what makes astronomy possible. So when we look at our sun's magnetic activity, magnetic fields are like pretty difficult to understand. And I say that as like a person who has tried like literally most of their life.
I agree with you as a science journalist who hates covering magnetic fields. Yeah.
Yeah, it's so challenging, and we can't really, we could see our sun in very great detail, as I mentioned, but still a lot of times the details of how it produces its magnetic field, some of that stuff is still in development, but we have a pretty good picture of it now. And so we know that at least for the bigger end of these like small stars, so sort of like beefier stars, still very small, much smaller than the sun, but the ones that are the largest are most similar to our star and probably generate their magnetic fields in the same way. The stars that are at the smaller end of that category probably have a little bit of a different mechanism for generating their magnetic field. But the big takeaway is that they all have these similar flares. In some cases, those flares can be like incredibly powerful relative to the amount of energy that the star puts out on a regular basis. But it still has some similarities to the flares that we see in the sun, in that, we see like bright white light. We also see X-rays and radio waves. There are probably, all these are hard for us to measure other stars. There are probably also coronal mass ejections happening. Oh, look at this amazing live stream. Those crescents that we were talking about earlier.
It's actually just a photo, not live streaming.
Yeah. Okay.
Yeah.
Well,
but I went over and
slowly.
actually managed to get a good picture of, and it's just going really well. We're definitely getting closer to where ours is going to max out here. So
that's so cool.
Yeah. So before we go any further, Lauren has told me, she's sent me lots of texts saying, I'm in annularity. I'm ready. So I think, Lauren, are you good to go? Are we able to see this?
Yeah, can you hear me?
Yes.
Yeah.
Can you hear me?
Yeah.
Yep.
Can you see my screen? I'm sharing my screen with you.
It's loading in
Is it
now.
Okay.
we're just kind of hanging out here waiting.
Get faster in my life. All right, let me try one more time. Welcome to live astronomy.
Live astronomy
it's
from the middle
showing.
of nowhere.
Yes. It's showing that I'm showing the screen. I don't know if it's working. I'm seeing the ring of fire now. My lovely partner is holding up my phone.
It doesn't look like it's coming through for us, unfortunately. That's a bummer.
Well, I have lots of pictures that I can send.
We'll need those because we're just big screen.
Everybody is cheering. It's pretty amazing. Sorry about that. Let's see. Let me try one more time.
Yeah, it looks like it's just nothing is actually coming through to us. So I don't know if the share's
All right,
actually
how about
working.
this? Hold on. I'm gonna.
I think the share is working. There's just not enough bandwidth.
All right, can you still see me as a person?
Yes.
Yes.
Through the Unistellar
telescope. Can we focus on her? Yeah.
I'm gonna make her slow layout. Here you go.
Yeah. Hey, astronomy finds a way. It is absolutely gorgeous. Yeah, it's I'm gonna move around just a little bit so y'all can see what I'm doing here. Wow, this is just incredible. So there's your ring of fire, y'all.
Wow,
That
that's
is,
so cool.
It's pretty
that
incredible.
is gorgeous. Wow, very nice.
Oh yeah, and you can
So
now
we'll
see it's thinner on the bottom than on the top. The moon is
wow.
It's moving
Oh,
across the disc.
moving.
That
so
is
cool.
excellent. Fantastic, Lauren. Fantastic.
A little bit more.
Oh, I can hear the applause in the background.
Yeah.
Yeah.
It's cool. Yeah, everybody's losing it. It's amazing. It's a little bit different than the total eclipse I saw a few years ago. It didn't get quite as dark here. As you can see, it still looks like daylight. But yeah, I mean, it's pretty incredible.
That is wow. And our stream audience is loving it. So we're getting some comments of great job and that's perfect. And so thank you so much
Will you
for
get out of the way. Go away. All right. Hold on, let me see if I can get one more shot in here. I mean, this is you make do with what you got. Astronomy doesn't wait for you.
This is true.
Yep. Yeah.
It's one of those,
So
when we started scheduling this. Go ahead.
No, I was just gonna say the moon is now starting to, cross the edge of the sun's disk again.
Oh, it's so neat though.
That's so amazing.
So I have a friend who commented as well in a group chat that was saying that it's amazing how bright it still is, even with most of the sun covered. And you could really see that in Lauren's video there. Most of the sun covered, it still looks like a regular daylight, which again, just to reiterate for everybody, why you don't look at the sun during a solar eclipse.
Yeah, were any of you able to catch the Ring of Fire eclipse that happened around 10 years ago? I think it was in 2012.
Yeah, I was. That's where I first managed to get these pictures of the leaves, and also I did a little pinhole projection that I actually angled onto my balcony, and I drew a heart in pins, and so I had a heart of little circles. It was really cool.
Oh, that's so cool. Yeah, I had the good fortune to go out to Bryce Canyon to catch it with a friend, and it was really, really cool. My first solar eclipse, actually. I'd never seen a solar eclipse, and I too was really surprised at how bright it is, even in totality or annularity.
Yeah, it was really neat. I mean, it's not getting dark here, really. I mean, the crescents are definitely cutting in, and yeah, it's not getting any darker here. So
I think it's actually drizzling out now for me. So
I don't think I'm seeing
wholeheartedly pouring in Chicago. So
yeah, I when I woke up this morning and the weather thing went off and said, it's supposed to be super cloudy today, and I said, oh, that's at least I'm on stream, so I'm not outside trying to watch this. So okay, I think we also have Franck back, who is stuck in clouds. So
no.
Yeah.
let's see.
How beautiful it is. Sunny, blue sky. Look, everybody is here.
Oh yeah, it looks great, Franck.
Yeah, we had an amazing time here.
I didn't.
In Oregon, there is always sun. The sun is inside, right?
Yeah. I didn't want to jinx it when you first got on, Franck, by saying that the sky didn't look amazing where you were, but I was a bit worried.
Yeah, well, if you don't try, you don't succeed. That's the point. And we wanted to be the first one to show it, but no time. Next was 48 in Oregon, something like that, right? So we'll be back here in 2048. You decided that you're going to meet here by then, and we are going to have another good time, right? But thank you for having us, by the way. She's here.
Hey, everybody. Thanks for coming out and seeing Franck and the clouds. So much appreciated.
And I don't know if Lauren still sees us, but we had a blast watching us being the stage of liberty of the year 2023. It was a very good symbolic moment, and we really love the fact that she was holding an iPad to show us the centrality while someone else in the background was holding for to make sure we have connection. I mean, that was, yeah, that was astronomy at its best.
Yeah, that's peak live astronomy right there.
Yes. Sometimes with the observations, people don't know that when we do major discoveries on ground-based telescope, we do things like that. I have memories of me entering in the telescope, it's a grand cage on the 3 meters above ground, just to hold the cable while we were doing observations. and the telescope was inclined, and I could probably have broke my neck if I was not holding myself properly. So with that all the time in astronomy, it's normal, okay? Not always clean. It's sometimes you have to improvise.
Well, thank you, Franck, for doing your best and being out there and for organizing all of this as much as you did. So
you did everything. We just were there. Okay. Thank you, everybody. I'm gonna go off and continue watching you on the YouTube in the bar.
Sounds like a good idea. To see you. All right, so Lucianne, one of the things you were talking about was how the red dwarfs are more common. How does the different type of star impact those? I don't like to use Goldilocks zones anymore because we're finding that that's not necessarily the truth. But how does that impact habitability?
Yeah, well, the first place that we would start is just to think about, again, the star as being like a kind of campfire that these planets are around. So, we have our star and, we're in the habitable zone of our star. And to your point, so are Mars and Venus, two places that are very not habitable for different reasons.
Right.
But at least for planet Earth, we, have this concept that there's a sort of rough area of light distance to be away from your star. We're getting the right amount of light that, if everything else works in your favor, you would be the right temperature to maybe have liquid water on the surface of your planet. Now, with these smaller stars, again, they're not putting out a lot of energy. They're, glowing, but very dimly. And so in order to get that right amount of light, you would want to be a lot closer to them, the same way that if your campfire wasn't going very brightly, you'd want to be close to them. And then for very large stars, which are also much less common than the sun, but are places that, we imagine might be able to form planets, the stars are burning very, very, very luminously and get a lot of energy. So in the same way that you would want to sit further back from a really bright bonfire than you would from just sort of a regular campfire you might build yourself, you would want to be a lot further away from those stars. Now, aside from the overall light, the other thing that is really important is the kind of light, the energies of light that you would expect to get from these stars. So here on planet Earth, again, we have a star that puts out most of its light in what is not very coincidentally the visible portion of the spectrum of light. We have a star that emits energies that our eyes are able to see. Probably because we are a form of life that evolved on this planet. There's a reason for that. We can see the light from the sun because it was the light that was available to us for all of life's development. There are different forms of life that have sensitivity to things like ultraviolet light, like bees, for example. But for us, visible light means the same energies that the light from the sun comes out at. The sun also emits light in the infrared, or slightly lower energy light that we're able to see with our eyes, and in ultraviolet and higher energy X-rays, which we're also not able to see with our eyes for the most part. Now, for stars that are smaller than the sun, they actually don't emit a lot of light in the visible portion of the spectrum. And so if we had, our human eyeballs on a planet around one of those stars, most of the light is actually coming out in the infrared. So you can imagine that that a creature that might, if you imagine a creature coming up and originating and then developing on a planet around a star like that, it would probably need to have eyes and, or if it was a plant, right, it would need to have photosynthesis that used different ranges of energy and light in order to be able to do all of its functions of life, like harvesting energy from the sun. So, and accordingly, also those very massive stars put out a lot of their energies of light in higher energy ranges than we get from our star. So it's really not just about the amount of light you receive, but also the kind of light that is available to do things that life likes to do, like be able to see, we are a form of life, right, that builds technology like solar panels, but also we have plants around us that use the light from the sun in order to make their energy. So, there's really this coevolution of everything that happens and develops here on Earth with the kind of star that we're around.
Well, I have to admit, it never occurred to me, and I feel very slow on the uptake on this one, that the light would be different from different stars, that we would not, if we were on a planet orbiting a red dwarf, we would not have visible light to see with. That, okay, you have just blown my mind a little bit. I didn't even think about that.
Yeah, it's really cool to imagine yourself in any of these places. And one of the things that I really enjoy about some of like the artist conceptions that come out anytime that we like discover a new planet around another star is that they're very fanciful and imaginative, right? But all of those like fanciful, imaginative imagery, all of that comes from the things that we know or are able to tell about that exoplanet system. And so, all of that then has implications for the way that we think life might arise and exist on these worlds. Take the example of photosynthesis. Plants appear green to us because they are reflecting green colored light, which says something about what energy they're absorbing in order to be able to, undergo photosynthesis, metabolize, take things like the carbon dioxide that we breathe out and turn it back into oxygen that, forms of life that like oxygen, like human beings, can breathe in. Then when you think about how that might work on a planet around a red dwarf star, well, then you mostly don't have the kinds of energy of light that photosynthesis here on Earth likes to use. So there are other channels of photosynthesis that exist, like red light photosynthesis, even on the planet Earth, but those might have to be quite a bit more common. You also could imagine that, if the plants only have red light to work with and they have to absorb it in order to do photosynthesis, then, and there's no other light around, then actually maybe they wouldn't reflect light at all and the plants might be black. So you can really have a great time kind of going down the imagination rabbit hole of what life might be like, or just the experience of walking around on one of these other planets.
Oh my gosh.
I think
That's amazing.
that is one of the things I most respect about astrobiology, is that one of the hard things is because we're so Earth-centric, it's what we know. Like you said, there's a lot of assumptions that we have kind of built in because all that we've ever experienced. And for astrobiology, you really gotta find those assumptions and get rid of them, because they just won't apply in a lot of cases.
Yeah, and I think there's this careful balance too, because sometimes people will ask me, well, why would you assume that all life would be carbon based? Isn't that very restrictive? And I think there's this careful balance between the things that we know about life on Earth in all of its many diverse forms, right? Are sure, in some sense, we want to be able to be sensitive to detect and explore and find life that it might be very different from life on Earth, but also the life that's on Earth is instructive about certain things that might be common to life everywhere. So in case of asking why life might be carbon based around the universe, astrobiologists aren't saying that oh, it's impossible that anything else could possibly exist. But if you look at the periodic table, right? The periodic table, and I wish that somebody had told this to me when I was in 5th grade science class and I had to see the periodic table, and I was like, this is boring. Why do I have to memorize that? But it's a list of how common things are in the universe. And the fact that carbon appears pretty early on that list means there's kind of a lot of carbon for people to work with, but the universe to work with, the chemistry of life to maybe make use of. And carbon is really good at forming these long, complicated chains of carbon atoms and other atoms that make up basic chemistry of life. long chains of carbon are not themselves life, but they are building blocks of life. They are things that life likes to use. And so, the fact we have, and we know from studying stars, how stars produce elements and create that periodic table, right? That you have a lot of carbon to work with. So it would kind of make sense that most life in the universe might be made from carbon because that's what's around.
Mm-hmm.
And so in that sense, the life that we learn about on Earth doesn't restrict us. It tells us something that might not be universally true, but might have elements of truth that are universal and that we could use in order to, recognize life when we detect it eventually.
So I'm going to be honest. That was my red dwarfs don't put out as much visible light. So if we were around a red dwarf, we wouldn't see invisible light. That was my moment just now. I have never thought about the periodic table as it is in order of amount.
Yeah. Because why would you? Because nobody teaches us that.
No, that is a fantastic. So I know we have kids that watch these. So maybe there is some fifth grader now who you have just instructed, and now they understand how cool the periodic table is.
Yeah, the periodic table actually very cool. Why don't they tell you it's cool?
So this is one of those things where it kind of astronomers like to tell you that it's hydrogen, helium, and everything else is a metal.
Yes.
But it sounds like for astrobiologists, it's hydrogen, helium, a bunch of stuff that can make life, and then everything else is a metal.
Yes, chnops. We call it chnops. Yeah, it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Chnops.
So it's interesting to see how the different areas of astronomy, astrobiology, astrophysics, how we all look at the table of elements. Now, I've worked, of course, in geology, and to geologists, it's like everything is important. You don't understand how much we need all of this stuff. So that's thank you for explaining that. I think for me, it also turned a light on in my head too. And now I'll make sure to tell my teenager that, so that he's gonna have to do a lot of OChem for marine biology. So
oh yeah.
Hopefully
and I'm sure
that sparks something. Makes it easier to get through, because OChem, everything I've heard about that is that it is a monster.
I took organic chem, and I have to say, I thought it was pretty cool. It's kind of like how, when you're growing up, you hear calculus used to mean like, oh, that's the really hard math. And then I got to calculus and I was like, this math is cool. Algebra is boring. Like, why do people just
why was I scared of this? Like,
yeah,
this
exactly.
is great.
So when I got to organic chemistry, I briefly in college thought that I wanted to double major in chemistry and physics until I remembered that human beings need to eat and sleep. And that like maybe filling every moment with a science class would not be great. But I got through organic chemistry, and the thing that I really liked about it is that you start to study like the three-dimensional structure of different like molecules. And I thought that stuff, like the fact, especially because like I'm an artist as well, and so the fact that there's like all these systems for like drawing things in 3D on 2D paper, obviously like we have computing and we could make models and stuff like that, but there's all this like shorthand for how you would like draw it in your notebook. And I found thinking about like this tiny like microscopic world and sort of the 3D as being really like fascinating. I will tell you actually, so I originally wanted to be a marine biologist when I was growing up, and obviously something changed and I ended up an astronomer. But a couple of years ago, I got to collaborate on a paper about solar activity and its effect on whales. So this was a paper where we studied the frequency of whale strandings in gray whales, and found that there's, at least we don't know what the causal relationship is, if there is any, but there is actually a correlation between the amount of whale strandings and solar activity. And the thought is that there might be some sensory ability on the part of cetaceans, whales, to be able to be influenced by the magnetic field of the sun, and like the way that increased periods of solar activity can create maybe geomagnetic effects here on Earth, that a lot of animals we know use magnetic fields on Earth to navigate. And so the thought is that maybe there is some influence from solar activity on whale strandings. Whale strandings are obviously very complicated. There's a lot of other things that are happening, like, cloudiness of the water in the ocean. But that was a really exciting paper for me because I was like, yes, I'm finally not a marine biologist still, but talking to them. But we wrote a paper together back in 2020, so it was very fun.
That's cool. I like that. That is really interesting. Please send me that paper. I want to read it now.
Yeah, sure. There was for anybody that's listening that doesn't want to read an academic paper, it was in the news at the time, I think early in 2020. And I think if you Google maybe like whales, sunspots, New York Times, you'll find something about that.
I can't imagine how during 2020 I missed
that. Imagine.
Yeah, it's not like that year didn't start off with massive fires in Australia and then it just got worse.
Yeah, the news cycle was kind of busy.
Yeah, a little bit.
I just think that's a very interesting example of how the sciences kind of coalesce, and there's a lot of interconnectedness.
Yeah, for sure. And astrobiology particularly, I think it's so interesting and exciting, especially the reason that I wanted to originally double major in chemistry and physics was because I never, I don't like having to choose. I like having a lot of options whenever possible, just like in my life. And so, I wanted a science that would combine all of the sciences, which is how I ended up in astronomy. And it was actually only later, because of the SETI Institute, that I learned more about astrobiology and ended up applying the things that I knew in astronomy to astrobiology and habitability and life in the universe. So, astronomy does use a lot of different sciences, but astrobiology is the ultimate melting pot of different sciences. So it's great. If you love a buffet, I highly recommend becoming an astrobiologist.
And we need them. You not only get to be a scientist, you get to be creative. So that's a fun place to be, and all respect to the astrobiologists who are doing the work. So Lucianne, thank you so much for being here today and for kind of jumping in earlier than we originally anticipated. It is always fantastic to have you here. How can people follow you? You are very active on social media, and so how can people follow you and see what you're working on?
Yeah, sure. I am Rocket2Lulu on just about every forum of social media. You can also find me at notnotrocketscience.com, and I'm not.rocketscience on Patreon as well.
Fantastic.
That's so cool.
Yeah.
Thank you so much.
Yeah, thank you so much for being here. And we're gonna jump over to some of our I'm giving Mitch the warning that we're gonna be jumping to him. I have seen a lot of people asking about the view from Austin. Let me bring Michael in real quick. I understand, Michael. Everybody, you're getting a lot of questions about can you back it out and see the full sun. What's the status there is? The answer is no.
The simple answer is no. The field of view on this telescope is fixed. So unfortunately, it's 27 by 37 arc minutes, and the sun is 32. So unfortunately, we can get everything in one direction. We can't get everything in the other direction. But you can I tried to center things so that we get as much as possible around the direction things are progressing. So I've been nudging it a little bit during the observation here, but unfortunately, we're trying to put a pound and a half of sun in a 1 pound box.
Well, you're doing your best, and I know Lucianne is probably very thankful because as they said that it's raining in Chicago, and
Go
I think it looks great.
They're not getting any of this view, and
that's right up there with Seattle and Oregon, right?
Right. Yeah. Exactly. All right, Lucianne, thank you so much, and we'll see you soon, I am sure.
Yes, happy observing. Thanks for having me.
Thank
Take
you
care.
for being here. Bye.
So,
All
we're
right.
about peak. This is about peak for me locally here. Right.
Yeah, that's coming in and looking great. I think mine is pretty much, from what I can see from the trees, it's definitely progressed. I'll have to take another picture, but it's definitely, so if this were the sun, my shadow is kind of like right up in here, and so it's mostly finished here. I think we're just getting to the end of it, so I'll have to see if I can get some more pictures. Mike Mitchell, are you? I know you're connected. Are you there? Can you show our screen? Your screen? Let's see. Calen was also supposed to be here, but Calen unfortunately had a technical issue. Yeah, unfortunately, Calen's solar lens failed him, and so we're not going to make Calen look at anything on screen because that would be bad.
Yeah. Yeah. Bad solar filter is a really good way to have to buy a new telescope or a new camera.
So here's Mitch. Hi, Mitch. How you doing?
Can you hear me?
Yeah, we can hear you. Welcome in.
I can't hear anybody.
Oh. Hi. So Mitch is in Texas.
I'm not sure
as
what
well.
happened. I was listening to everybody, and now I can't hear anybody. So,
oh no.
Anyway, if you can hear me, I'm in Boerne, Texas, and the Ring of Fire just ended. I'm not sure how I can show an image of it on here, but we got a crowd of about 20 people here at the Fairfield Hotel Marriott property here in Boerne, Texas, and we had quite a crowd that enjoyed the Ring of Fire, and they played the Johnny Cash's song "What Was Going On," and it was pretty neat. I'll see if I can show a little bit, see some of the crowd here.
Oh wow,
it's a nice turnout.
But
yeah, I think
also I had 3 telescopes set up. I had 2 imaging telescopes set up in the windscreen behind me next to the pickup there. And then I had an optical telescope set up here that people could look through. Plus, of course, everybody had Eclipse glasses. So I still can't hear anybody. I'm not sure what happened to my audio, but so that's about it. I got some good images, I think, but like I said, I'm not sure how to show those in the in this program, and I still can't hear anybody. So I'm going to be quiet and let you guys get back to it.
Oh, it's unfortunate that he can't hear us,
I
but
know.
he did give us a good view of everybody there, which I think is also one of the neat things about solar eclipses is that it really is, you get a little community everywhere, people coming from wherever they are to see this event, and you're never without friends at one of these. Everybody kind of, if you have technical issues, your telescope doesn't work, that's fine. Your neighbor there, they're going to help you out because everybody wants to see this.
I definitely, when I started bringing my telescope to things, I definitely had a handful of people who were like, oh, here, let me show you how to do this thing, and here's another trick for it, and you should get this. And so it was very helpful to have that community guidance, and it is a very, it's been a very welcoming community, so I really like it. And Marianne Pugh Fernandez has said that it is pronounced Boerne, not Bourne, so it is Boerne, Texas. So very cool. Thank you. And thank you to Mitch for popping in. And Mitch, if you ever do get to hear us, you can send pictures our way and we'll share them. So thank you for being here. And all right, I'm gonna bring Michael back in because Michael's getting real close to
yeah, we're actually just past the peak at this point. And so I was just going through and nudging things a little bit outside so that, we can kind of go with where we are now. But I've got, got some interested neighbors checking out the tablet I've got outside. And my son's out with his the DSLR taking some pictures there. So I'll be sharing those later too.
That's cool. So I actually wanted to ask you how the eVscope. So this was a recent addition. The eVscope is actually now able to track on the sun. Have you had any problems with the moon being in the way? Did the eVscope get confused? Because I know Lauren right now seems like she's having issues actually getting on to the sun.
Yeah. If I was going to bet on it, yeah, I mean, I got myself tracking way before the eclipse started. I've been tracking live since about 9:30 local time.
Yeah.
I think part of the thing is that the software that's figuring out where the sun is assumes it's round.
That's a good point.
If you want me to bet money as a software,
that's a good point.
As a software guy, that would be as a software guy, you've got my best guess. Okay, is like that can't be the sun. It's not the right shape.
That's a donut. That doesn't even make sense.
Well, that's definitely not the sun.
Well, that's cool. I'm glad you got on it before, because it is. It seemed, I saw at one point it seemed like it lost tracking, but the fact that it hasn't. It hasn't been moving off of the screen unless you've been just dynamite at nudging it.
Well, I've been doing a little bit of nudging just because, like I said, I've got the problems of my field of views. 27 minutes, and I'm looking at a 32-minute target. But actually, and that's one of the things I've been really impressed at is not only has it maintained tracking, rock steady on its own, but I've been able to do these little nudges, and it didn't lose tracking. It's maintaining tracking. So that was one of those things where, like I said, I was a little like, should I mess with this? The old saying about, but you should never do anything during a demonstration that you haven't done.
If it's not broken, don't try and fix it.
I just had this unfortunate problem that I haven't had a convenient eclipse to try this out on before. So
it's true. I mean, it is true that it's not exactly like these come around all the time. So
right, but like you said, this is a very new feature, and honestly, I mean, I've been doing some solar observations with it, and it's been working out really, really well. And I honestly was a little curious as to what was going to happen during this eclipse, just because of how much of it was, how much opportunity there might be for it to get confused. Right, just because the sun stopped being the right shape, and if it's saying, well, where do I put it? So it's really worked out quite nicely. So, but
yeah,
definitely,
I'm glad.
For the sake of the folks in the comments stream, I'll make sure that by the time we do this again, maybe I have maybe I'll get a scope with a wider field of view, so we don't have anything hanging off the edges. But if you guys want to help me out with that,
I really like this view. I feel like we really lucked out with you having your setup and having such clear weather, because this has been absolutely gorgeous. And knock on wood, we haven't had any problems with it. It seems like the connection's been great.
Yeah, this is.
Yeah, well, I've got QuickTime recording the stream from the scope also. So whatever we want to do with that, that'll be available as well.
Oh, good. Franck wanted to know if you were, saving anything, keeping the pictures and that kind of thing. So that'll be great.
Okay.
All right. Fantastic. Let's see. Looking at my schedule, we've talked to Mitch. Mitch, can you hear us now? Do you want to come back on? And while that's happening, I'm going to answer this question. Melanie is asking, will this be available to watch later? Yes, absolutely. Check out our YouTube channels. It'll be a video on demand on Twitch. It'll still be on LinkedIn, and it'll still be on Facebook. It'll still be on Twitter, but you'll have to scroll through our feed to get to it. But it pretty much stays everywhere else. So yes, absolutely. You can come back and watch this later too. And also thank you for telling everybody to hit the like button. Much appreciated. Like, subscribe, share with people. All those things.
Boost.
Yeah, give us a boost. And I really want to give a quick shout out to the folks at Explore Scientific who are also streaming us. So thank you for letting us throw ourselves on your YouTube stream as well. Much appreciated. And you can also check it out there. And if you're watching from that stream, thank you for being here as well. I think we're just waiting. We've I don't know if Mitch can hear us, so I think
I don't think you can.
I don't think he can. I don't see Athena here yet, so hopefully we'll get Athena soon. And yeah, and then
right.
We're waiting for Homera to come back too. So
I will. Oh yeah. Just in the meantime, while we wait on people, there is one question that we start that I think is very interesting. I kind of wanted to talk about that for just a few minutes. Jezri on YouTube asked if annular eclipses are going to be more common in the future. And this is an interesting question because you would think that why would they? But yeah, they are. Over time, the annular eclipses are going to be what we see more and more of because the moon is actually getting further away from the Earth. There's the thing on. So as the moon orbits the Earth, is starting to steal some of the angular momentum, so the rotation of the Earth. When it does that, it moves farther away. So by the time that the moon has finally reached a point where it is orbiting at the same speed as the Earth and is no longer stealing our rotation, it will be far enough out that all we will see are annular eclipses. So yeah, not on time scales of our lifetimes by any means, but way in the future, that will be all that people are able to see, and no one will get to experience a total solar eclipse. So all the more reason that if you can see a total solar eclipse, go out of your way to do it because it'll be a rarity in the future.
That's in April, right?
Yep.
Next
yes.
one.
The next one is in April of 2024.
And I have the good fortune of the fact that it'll also be visible from right where I am right now too.
Oh, me too. That's awesome. I'm in my backyard. I can see it.
Wild seeing the two tracks on the map cross.
Yeah.
And where it crosses like just west of here. So
that's fantastic.
You're Austin, I see.
Yes.
Nice, right on. I just moved out of Austin. I'm up in the Dallas-Fort Worth area now.
Okay, great.
Yeah, also was able to see a great view of the eclipse. This is maybe from my eVscope. It was amazing. I still have my phone recorded right there too. I'm able to attach a little solar filter to it. So we're just live on Instagram. So I'll keep this up.
Good times.
So let me welcome Athena informally here. Athena is known. This is Athena Brensberger. She's known as AstroAthens on social media. She's a science communicator and an astronomer, and you're definitely gonna be seeing more of her around. I think because she's now done one thing with us. So guess what? Now she's gonna do more. So welcome Athena.
I'll bring no energy.
Yeah, that's what we need. I'm getting too old for that kind of energy. So cool.
On the West Coast, right? So it's like super early by you guys. Yeah.
This is not untrue. I know for a fact Ryan has an entire coffee pot not far away from him right now.
Yeah, every time I have disappeared from the stream for a minute, it's because I had to reach down to get a coffee pot and fill up my cup. I realize now I maybe am a little over caffeinated, so I'm moving back to water.
I had the thought of my wife making a terrific coffee run for a major brand of coffee.
Oh, nice.
Yeah, thank you. We don't want to have to go back and censor that out because
I covered everything.
So we all do a cheers with our coffee cups.
Yeah,
I just have water, so I'm down to water. Y'all probably saw me with my my soda can earlier, but now I'm resigned to water. I've decided to not over caffeinate myself. So Athena, tell us about yourself. Tell us, how did you get into this? What's your focus in astronomy, and how did you end up doing science communication?
Yeah, I always loved space. I grew up in Brooklyn, New York, so I was lucky to see like 2 stars in the sky. So I really didn't have a lot of exposure to the night sky until I actually moved out to Texas. But fell in love with the stars when I was like 11 years old because of a book I got of images from the Hubble Space Telescope. And I was mind blown when I found out that all of these things, like on my sweater, are out in space. There's things like galaxies, millions and billions of stars. And I just had this thought at 11 years old. I'm like, well, if there's all these stars like our sun, and probably all these different planets, there's got to be life out there. And so I've just been like so preoccupied with SETI, the SETI Institute, like trying to find life beyond Earth. And I just knew I was like, I'm gonna have to pursue a career in astronomy some way or another. I gotta be doing research. I want to find out if there's life out there. Then I fell in love with everything else that has to do with space. And then I just started communicating it in like 2016. Just was like, maybe I should start a YouTube channel and start sharing what I love and things I learn along the way as I'm earning my degree. And that's what's kind of led me to where I am today. Still talking about space, getting excited about these things. That's a little blur.
Yeah, I think that is very cool, and I love how easy it is for astronomy to be something that people get into, because it is an inherently cool science. Not to knock all the other sciences, but I think it's one that everybody is really interested in, even from a young age. So I think science communication from astronomers is a big important point. So thank you for getting into science communication as well, because I think that is something that is needed as time goes on. So people can see that science is cool.
And we need the enthusiasm and the knowledge. And I really appreciate the fact that social media has made this so easy to put this kind of information out there. And thank you to all of the YouTube and Insta and TikTok streamers and video makers who are doing all of this. There's so many. I couldn't even begin to name them. So, Athena, you are in very, very good company, I know. And so, we're very glad that you are one of those ones who has jumped in on that. I like that.
Space gal, also Emily Calandrelli. She actually just joined my Instagram live and was like, I wish I could see it from where I am. And she just does such an incredible job with everything she's doing and her children's books. But I really got inspired by Dr. Charles Liu and Neil deGrasse Tyson. They were some of my first mentors in New York. And Dr. Liu, he if you don't know who he is, you've got to check him out and his research. But he came running into the classroom the first day of astronomy, like 101, jumped on the table and was like, who wants to learn about space? And that just filled my heart with so much love for space. And I was like, I want to be like him when I communicate science and astrophysics to the world, because it just got everyone to wake up, pay attention. And space is just such a fascinating topic that it doesn't take a lot to really talk about how glamorous it is and how awesome it is. Again, referencing the sweater, shout out to Sartorialist for it. But it's such a beautiful science, really is.
Yeah.
So happy to be here.
And I definitely my experience. I had an astronomy and astrophysics professor tease me a little bit, because when I'm in class, I'm very much head down, taking my notes and doing all of the things. And then we had a star party. And it was like he said, I watched a switch come on, and all of a sudden you went from this like studious, head down, heart, answered questions but didn't talk a lot, to like basically roping people in and bringing them over and going, look at the thing in the telescope, come on, And so, and we were doing a solar astronomy, so it was the middle of the day, and it was like, come look at the sun, it's safe, we've got a filter, come here. And everybody was just shocked by the change in personality, because once I'm out communicating these things, it's a blast to do, and it's easy to get people excited.
It really is. Yeah. Especially when there's like kids around too. Like they just get so excited. They have the best questions. I love working with kids. And it's just like, yeah, they've been the ones who've asked, I think, like some of the most scientific questions, just like the big whys and hows, especially the ones we don't have answers to yet. That's the exciting thing. So you get to plant the seed of like, maybe you can be the one to discover that one day. So I love it. Yeah. Oh,
all right.
amazing.
Well, thank you, Athena, for being here, for showing us your picture, and for also live streaming on Instagram. Much appreciated. You will see more of Athena. I think I'm gonna try and drag her into a few more things. So I suspect this is a person you'll want to get to know, and make sure you follow her on social media at AstroAthens, and
like the city in Greece.
And you'll see a lot of cool stuff. All right,
Awesome.
Athena, thank you for joining us, and lovely to have you here. Lovely to meet you, and have a wonderful rest of the day.
Thank you so much, everyone. I'll see you guys next time. Enjoy the eclipse. Bye.
Bye.
Bye, guys.
All right. we have our next person here, and that is Homera. Hello, Homera.
Hey, how you doing?
Good. How are you?
Fantastic. So lucky.
So,
Howdy. Just 2 weeks.
oh no. Where are you at?
Tampa, Florida.
And you got all clouded out?
No, it's perfect. This morning.
Oh, it's perfect.
Yeah,
oh, fantastic.
Let me show you real quick how it is.
Beautiful.
In the meantime, let me show you my setup. Unistellar telescope, as you can see it, and right there.
Oh, nice.
That will prevent the overheating of the sensor. I had to improvise.
Oh,
yes.
That's a good idea. So, did you make your own solar filter there?
Kind of, yes. I ordered a new another one from Unistellar. We get it pretty soon. But I purchased the from 1,000 oaks, I think it is, which is approved for that, and it's working perfect. Let me give you an example of the picture. Yeah.
Oh yeah. Oh wow.
That's
nice.
Great.
Is that current? That's right now?
That's correct. Yeah, that's right. No, one more time.
Oh, that's gorgeous.
Mm-hmm.
Very nice. So how?
Yeah, go ahead. Sorry.
How easy was it to get everything set up? How was that for the process for you?
I've been reading in the chat and listening to you guys. It's been very helpful. But I also had I used to have a PST. I do mostly sun, watching the sun through a computer. At Coronado, I had a Coronado PSP, so I'm kind of familiar with observing the sun. Actually, it's my favorite because it's the dynamic. There's always something different.
Mm-hmm.
With this Unistellar and the filter they came out with, can't wait to use it because I would like to do live streaming.
Oh, that would be fun.
Yes.
That would be great.
Absolutely.
So do you have a handle, social media that people could maybe find you under when you do live streaming?
No, actually do it through Facebook.
Okay.
Yeah, I don't have time actually. I just gotta do it my days off.
Oh yeah, fair. So it'll be more of a personal thing. That'll be fun.
Exactly. Yes, that's correct.
Well, your friends and family will get the honor and privilege of enjoying that. So congratulations to them because they will have a good time.
Absolutely. Well, thank you for having me.
Yeah, thank you for joining us, Homera. Much appreciated. Enjoy the rest of the partiality that you have, because you're just a little bit behind the rest of us. So
yeah,
mine is done. I have no shadows anymore. I have no shadows.
Yeah, I think to take a moment just to say thank you again, Homera, but to all of the other citizen scientists and speakers who have come in today. You've all donated your time to this, and you've donated your time not just for us, but for everybody watching. So thank you so much. Great experience.
Thank you, guys. Take care.
Thank you so much. It's been an absolute pleasure.
Yeah. Thank you. All right. Thank you, Homera. All right. Wow. So we're kind of. It feels like we're closing in on this, but we still have like 40 minutes left.
Oh yeah. Yeah,
so,
we're not done.
We're not done. We're not done. We still have one more major guest. So very excited to welcome this person in. And so that's my warning to him in the background that I'm going to be adding him to the stage. So let me welcome in, and we're a little bit early. This is what happens when it's live astronomy, but welcome in last, but definitely not least. Our final guest for the morning is research scientist Doug Caldwell. Doug is currently a pipeline support scientist for NASA's Transiting Exoplanet Survey Satellite. You may know that as TESS. And prior to that, served as instrument scientist for Kepler, which is really cool. Doug specializes in star formation as well as extrasolar planet detection and observation. So hello, Doug. Welcome, and thank you for joining us.
Hi, thank you. Thanks for having me. This has been very cool, and especially cool to be able to see it on the screen here because it's pretty cloudy here. As you probably know, Beth, I'm just down the road in Santa Clara. So
yeah, I'm in San Jose, so I'm actually south of you, and I got some good shots from the leaves, and that's been about it. So
cool. Yeah.
And it sounds like, Michael, you're getting some interference from leaves here. Is that what you said?
Yeah, I said it, unfortunately had to worked out pretty well, but not quite perfect here. We did well as far as getting most of the way through this before I started ramming into leaves. But I'm not afraid to move it at this point because I'm going to be like, oh, is it going to come back? So.
Thanks, Michael, for your excellent shots the whole time.
Yeah.
No problem. My pleasure.
Yeah, no, I'm really glad that we got that worked out last night and that this ended up working as well as it did, because obviously Franck is totally clouded out. Ian never managed to make it on because the internet just never functioned, and as we've seen, Lauren has had her struggles as well. So that was very cool. Much appreciated, Michael, that you have been able to stream this the entire time. So
Homera was very good too. So
yeah, thank you, and thank you so much for being here. We're going to focus on Doug for a little bit, but we'll have you in the background and back on in a few.
Yep.
Cool.
All right, so Doug, let me put you up here. I'm gonna make you a solo. Tell us about yourself and what you do and your research.
So I'm an astronomer. I got my PhD in physics and astronomy at RPI, Rensselaer Polytechnic Institute in New York, and I've been working for a bunch of years now on looking for exoplanets from a bunch of different locations. Pretty much all by the same technique. And so we've been using the transiting method, which the stuff we've seen today is just, I heard you talking about a little bit about it earlier, is just the ideal introduction to this. This eclipse viewing is really just a microcosm of how you do transit photometry to detect planets. And that's basically looking for the shadow of a planet passing in front of a star. And so this is exactly what we're doing. I think today we've all been able to reliably detect the fact that there is some additional object orbiting between the Earth and the Sun, and that's exactly how we do transit photometry. It's a little bit harder because the stars are further away, but it's the same idea. So that's been very cool to sort of see just exactly how we do this. And it's also interesting because it shows a lot of the same complications that we have. So that's cool.
So when we talk about, you use the transiting method and using the moon as an example. So the moon is passing between us and the sun. So it's, that perfect alignment. And in this case, it's cutting off almost all of the sun's light, but not quite, right? I think annularity, peak annularity was about 94% for most people, for people who were there. What kind of percentages are you dealing with in an exoplanet transit? Because they're certainly not 94%, are they?
Not usually, no. In general, if we're talking about stars the size of the sun, which is what we're seeing here, then a Jupiter-sized planet is about what we see is essentially the area of the planet divided by the area of the star is the amount of light that gets blocked. It's a disk moving across. So the area of Jupiter, the projected area, is about 1% of the sun. So if Jupiter goes in front of the sun, seen from a long way away, the light drops by 1%. So that's doable. I mean, people have done that with better with unistellar scopes and with other telescopes from the ground. It's not trivial. You have to be careful and control what's going on in the atmosphere and clouds and make sure your observations are good, but it's doable. If something like the Earth goes in front of the sun, that the Earth is about 1 part in 12,000 the size of the area. So the signal we use I remember the number from Kepler is 84 parts per million, or think about 1 part in about 10,000 of the light gets blocked. That's not doable from the ground. That's very hard and is even hard to do from space, given big telescopes like Kepler, which was about a 1 meter telescope. And so that's the kind of problem if we're looking for Earth-sized planets around stars the size of the sun, that becomes much harder. Now you can take advantage of the fact that, like Lucianne was talking about before, most of the stars in the sky are actually much smaller than the sun. So the same Earth-sized planet makes a much bigger signal. And so if you look for Earths around M dwarfs, you can get a much bigger signal. And that has been done from the ground in some cases for particularly nearby bright stars, where we've seen small Earth-sized planets orbiting, like the TRAPPIST system has a bunch of small planets orbiting. It's around an M dwarf, and those were detected from the ground by relatively small telescopes.
So
Wow.
you've worked on both Kepler and TESS. Can you tell us what the difference is between the two missions? What Kepler set out to do and what it accomplished, and what TESS is doing now?
So Kepler was conceived of a long time ago. Actually, originally sort of in the 80s by Bill Barucki, but really designed in the 90s when we only knew of a few exoplanets. And so in 1995, the first exoplanet was found around a star kind of like the sun. It was a big Jupiter-sized planet. And Kepler had already been pretty much designed by then. And the idea was, if you have planets orbiting stars, the way they were being detected then was through this radial velocity method, where you're detecting the gravitational tug of the planet on the star and looking at the frequency change of the light from the star, like analogous to an ambulance siren coming towards you on the highway and then going away. You hear it high-pitched coming towards you and then low-pitched going away. The same thing happens with the light of the star. And so that had been successful, but the idea behind Kepler was, well, you also could see if these planets happen to pass in front of the star, like the moon is here, you could see the star dim a little bit. And that would let you look at a bunch of stars at once if you took a big picture of a lot of stars at once and just stared at them. So Kepler's goal was to stare at a lot of stars, and by a lot at that time we were using 170,000 as our sort of target number for Kepler that we monitored for as long as we could. And we wanted to be able to see planets basically the size of the Earth orbiting stars like the sun in orbits that would make them this is, as Lucianne mentioned, I think this is very complicated, but would make them potentially habitable. And at the time, the thinking was, oh, you're just the right distance from your star, so that the temperature could be good enough to have water on the surface. So the Earth is one example, right? So in a 1 year orbit around the sun, we can have water on the surface of this planet, at least for a while, until our greenhouse gases get too bad. So we wanted to be able to see a 1 year orbiting Earth-sized planet around the sun. So in order to see the transit, you don't know when it's going to go in front of its star. So you need to look for a full year, and then you'll see one event. That's not very good, because you could have been anything. Could have been a rock going in front of your telescope. So you really want to see at least two, and then that gives you a period. But that's still some uncertainty. So if you see a third one at the same spacing as the first two, now you've really got, oh, this is a periodic thing. So 3 is sort of a minimum that we wanted. And so Kepler was designed to look for at least 4 years to add in some assurance, and stare at stars with precision enough to see Earth-sized planets. We didn't know if they were out there. And so Kepler was a survey. It stared at one spot in the sky for basically 4 years until it had some mechanical problems, and did this survey of 170,000 stars, basically to take a census of what kind of planets were out there. And so I checked in this morning on the NASA Exoplanet Archive, and there's something like a little more than 5,500 confirmed exoplanets known. So from 1995, when we had the first one, we now have over 5,500 that we know of. So it's been an amazing explosion in this field. Of those 5,500, something like 4,100 or so were found by the transit method. So this method has been extremely successful. And of those 4,000, I didn't actually do the accounting, but over 2,000 of them, I think close to 3,000 of them are from Kepler. So Kepler was this amazingly successful survey mission that just showed us that it showed us really two key things. The first one, I think, is that we know now that there are more planets than stars in our galaxy. And we know that something like the number has some uncertainty on it, but something like maybe 10 to 60% of stars that are somewhat like the sun have planets that are in the rocky size zone, so sort of around the size of the Earth, in orbits that are potentially habitable. So that's, even if it's 10%, even if it's 1%, there's 200 billion stars in our galaxy. 1% of 200 billion is a very big number. There's a lot of planets out there that are interesting for understanding habitability, and Kepler showed us that. So that was Kepler's goal.
Mm-hmm.
Because of the way it worked, sorry, this is becoming a long answer. Because
no, it's fine. It's fine.
It was looking at these stars that mostly were far away, and so when we found a planet, we couldn't do a lot of detailed study on that planet because the stars were relatively faint. What TESS's goal is to look at around the entire sky instead of staring in one spot, and find all the nearby planets around bright stars, so that we can do a lot more scientific follow-up on them with, for instance, JWST. And so TESS's job is really to not survey and count how many planets are, but find all of our nearest neighbors. And it's doing a very good job at that too.
So Kepler was definitely the thing that got me into science communication. That was the first NASA socials I did, were still called tweet ups back then. And I did a lot of them at NASA Ames when Kepler launched, when Kepler went online, when we started getting data from it. So it was, I like to say that Kepler kind of like gave birth to that sort of thing for me. And TESS, so one of the things I know about TESS is that TESS was supposed to sort of like work not quite hand in hand with JWST, but that was a lot of, okay, when TESS is going up and it'll have JWST to do these things. And then you didn't have JWST right away. So you guys are finding, more exoplanets yourselves. It's not just a follow up on things that were already there. You're also like finding new exoplanets. How does that, is TESS using the same method? Is it also the transit method?
TESS is also using the same method. It's a very similar. Conceptually, it's the same as Kepler. It stares at a patch of the sky for, instead of 4 years, it stares for about a month at a time, and then it's in an orbit between the Earth and the Moon. I don't think we'll see it today, but and so it stares for about a month at one part of the sky, and then it points to the next segment, and then the next segment. And in the course of a year, it covers the entire sky. And the way we've operated is it has 4 cameras that are arrayed in kind of like a fan. And so it started off actually looking in the southern hemisphere. It looks at this segment and clocks around the sky. In a year, in the first year, it covered the entire southern sky. Then it flipped upside down or right side up, depending on your perspective, and did the northern hemisphere in the second year. And now it's basically just been repeating that. And so we're going back and revisiting the stars we looked at before to either, get more information on ones we already knew about, find new planets, find longer period planets. So it's just sort of doing this ongoing survey.
And is TESS an extended mission now, or are we still in the initial mission range?
It is in extended mission number 2.
Wow.
So, and extended missions have been 2 years each, I think. So actually, I think it just started year 6 of observations.
Time flies.
Like in, has it started yet? Maybe it starts this month. It's right around now. So, yeah. So, it's doing really well. There's no indications of any issues with the spacecraft. It's got plenty of fuel. I think they put enough fuel on it to last for 25 years or something. And so, barring either NASA cutting the funding or something catastrophically breaking, which we don't expect, hopefully, it should be able to keep going for a very long time.
That's great.
And go ahead, Ryan.
Oh, so I was just going to say, Zap fan on YouTube brought up a good point for maybe that people that are too young to remember how phenomenal the Kepler and TESS missions have been, causing a paradigm shift, essentially. I remember before Kepler launched, there were only like 400 known exoplanets, and there was a real question of how many are we going to find? And Kepler gets up there, and it just immediately starts finding exoplanets everywhere. And it really changed the game. Really let us know exoplanets are not uncommon. They are all over. So I just didn't want to let that pass by because I think that's a very cool idea. And I think a lot of people probably don't recognize exactly what it was like before Kepler and TESS missions happened.
And, I mean, one thing about Kepler that I often sort of put out of my mind or forget is, Kepler and TESS both, and just like our eclipse here, we only see this event when the planet is lined up perfectly between us and its star. And so most planets orbiting stars out there don't do that. And so the fact that we see one means that there are a bunch of other ones that we're not seeing because they're not transiting. And so we can make that correction for how many planets are really out there based on the fraction we're seeing.
Yeah, that's a great point.
And I think one of the other really amazing and fascinating things that kind of came out of all of these exoplanets is the fact that it's sort of like Lucianne talking about how we have this one example of life on Earth, and that's what we kind of have to use as sort of our basis for astrobiology thoughts. We also only have this one example of a solar system when we started out, and of a stellar system, and so we're like, okay, we have so many planets, we've got asteroid belt, we've got we've got the Kuiper belt, we've got an Oort cloud, and then we started looking at all these other exoplanets, and it's sort of like, okay, all of our planetary formation and evolution theories are just broken. Where they're just broken now. Like we don't know. Like Jupiter's can orbit really close to their suns. They're kicking things out of their solar systems. We have rogue planets, and it's sort of, it opened up this whole thing of, okay, yeah. So when we only have one example, it's not necessarily the typical version of everything else out there.
Yeah. And I think as Lucianne pointed out, we don't even live around the typical star.
So what for you has been the most amazing or interesting discovery that has happened with the advent of finding exoplanets?
I mean, just the sheer number, of course, has been really cool. One thing that I think kind of surprised me, and maybe if I thought about it more carefully, I would have expected it, was the number of planetary systems that Kepler and also now TESS have detected, where we're seeing not just one planet transiting its star, but 8 in some cases, or 6 or 7 or 8, and so we're seeing these systems of many planets, and that again, it's not unexpected. Why would they only have one planet? We have 9 or 8 or however you want to count. But the fact that we've actually seen them, and there are a bunch of them that are transiting, and so that means they're lined up very flat in their solar system, flatter than our planets are. Like if we were looking back at our solar system from far away and we're able to see Earth transit, it's unlikely we would see even Venus transit, only if we happen to be lined up along the sort of the line of nodes where their orbits cross, because their inclinations are inclined a small amount, but a couple degrees, enough that they wouldn't both transit generally. And so the fact that we're seeing some planetary systems with 7 or 8 transiting planets means these systems are really, really flat, and how those formed and how they stayed like that after presumably many millions of years is an interesting problem in planetary dynamics and formation, and I think that's informed a lot of ideas of how these things came about.
Yeah, the idea of hot Jupiters has always been interesting to me. Is how do you get a gas giant that is so close to its parent star? And the idea that they're migrating in as the solar system forms. There's a lot of interesting questions about solar system formation that exoplanets inform us on.
I think another thing that Kepler found, that I don't know if people are aware of, is that the most common type of planet Kepler found was what we're, for lack of imagination, calling super Earths or mini Neptunes, this planet in between the size of Earth and Neptune. And we really don't have an idea what they're like. Are they giant rocks? Are they small, icy, gassy balls like Neptune? And they're the most common thing we've seen. And we don't have one, as far as we know, in our solar system. And so what are these things? And, are they like great places for life, better even than Earth, or are they not? And so it's just an interesting,
And that also led to that mass gap too, right? Like there's a spot sort of in there where we haven't actually seen exoplanets at like that 2 times Earth size. It's always like 2.5.
Yeah, there's a space.
Yeah, and so when you look at like the histogram of it, there's a gap in there of planets we don't actually see.
And one of the ideas is that they're two different kinds of planets. One is big planets that started out like Neptune and got really close to their star and essentially got evaporated down to a certain size and stopped shrinking. And one is planets like the Earth that can only get so big and still be like the Earth. And there's a spacing in between those two things. And so that's, people are trying to tease out, can this tell us about how these things actually form and evolve?
I like the fact that we have so many exoplanets discovered at this point that when there's a press release about a new exoplanet, there's always something weird about it now. It's like, okay, we found this new strange thing going on. We don't know what's happening here. This one,
the
like
planet of pure diamonds.
Yeah, this one is pure diamonds. This one rains molten iron. I mean, there's just, it's always, now the press releases are always like wild and bizarre, and it's really cool.
It's fun. It's been a very exciting field to be in. I've been very fortunate to have entered this field when I did and been involved in the projects. Especially Kepler has just been amazing.
So now that JWST is up and running and you can actually do the things with tests that people wanted to do from the beginning, are you working on JWST at all? Have you submitted times for that? Do you have like a list of planets that you're all just trying to get time for?
So I personally have not, and I'm like thinking like, oh man, I need to be doing this. I've been still working a lot on tests and trying to understand the results from tests in Kepler. But I think that's the future of this field, and we now know there's a lot of planets out there that could potentially be habitable. Well, now let's go see, are they habitable? And for one thing, Kepler and TESS find all these planets that are they're about the size of the Earth, but we actually have no idea from Kepler and TESS data if they have an atmosphere even. And so one of the things JWST can do is go and actually detect gases in the atmosphere. And people have done this from ground-based telescopes and Hubble to some extent also, but JWST will be the next bigger, better step in that. And once we see, oh, this planet does have an atmosphere, in fact, we can see it has methane and oxygen in its atmosphere. We can start to get ideas of, okay, not only is it potentially habitable, but maybe there are actually signs of evidence of life. Like you have gases that are sources of biology, or caused or brought about by biology. And so trying to figure out what are good, what we call biosignatures, indicators that there might be life on that planet. And JWST is just at the verge of starting to be able to do that for some bigger and sort of key planets. NASA's thinking about what's the next big telescope, bigger than JWST, that could actually do this for kind of Earth-like planets, Earth-sized planets. And it's it's hard enough to detect these things where their size and their signal is 84 parts per million. It's even much harder to characterize them and figure out, oh, what's in the atmosphere of this thing with this tiny, tiny signal. And that's what JWST and these new planned telescopes will hopefully be able to do. And it's even harder at that point to interpret what you're seeing and decide if it means if there's life or not. And that'll be up to that's coming along down the pike, I think, though.
Yeah, we've definitely already seen some papers analyzing a couple of the TRAPPIST-1 planets. And also, we talked to Niku Madhusudan a couple of weeks ago about Haitian worlds and finding these, different types of planets and it may have a biology signature, but it's going to be hard to tease out, and we might never know with any real certainty. So those things are starting to come along. So that's great. Doug, one question for you also from Zapfan, asking, are there any examples of small rocky planets in orbits that are outside the orbit of a hot Jupiter?
Not that I know of. I'm trying to think of other detection techniques. One of the complication is, small planets are hard to detect. The further away they are, they're even from their star, they're even harder for transiting photometry. That means they're less likely to transit because their alignment has to be better. Also, their orbital period would be 11 years or something. So we'd have to we'd have to have seen, been looking for 22 years or more to see them with transits. With radial velocity, they don't have enough mass to tug on their star. And I think with direct imaging, they wouldn't be bright and hot enough. There's another technique, which I won't go into in detail, but it's microlensing, and it's essentially the planet blocking the planet and the star, bending the light from a distant background star as it goes past this star and planet in between us. And those can detect small planets, and they are more sensitive to wider separations. And so there's a telescope that's being built now, the Nancy Grace Roman telescope, that one of the key goals of its mission is to do a big microlensing survey, and they should be able to detect these small Earth-sized planets in orbits that are around. I think they're pretty sensitive around sort of Jupiter 5AU orbits. So I think we'll have an answer to that question probably in 5 years or so. I forget when it's scheduled to launch, but it's relatively soon.
Yeah, relatively soon.
Yeah.
We work on astronomical times, so like relatively soon.
Sometime in the next decade, maybe.
Yeah, exactly.
Yeah, definitely in the next decade.
Yeah, there are a lot of things where it's like it will get there in 6 years. Okay,
they're actually building instruments and stuff for it now and testing, so it's happening.
Fantastic. Well, Doug, thank you so much for joining us this morning. I'm glad we could also show you some eclipse, since we're in the same position as the rest of us on screen here and not really able to see much. I did see some pictures coming in from the San Jose Astronomical Association, so hopefully I'll get some of those out on their feed later today.
I got a cloudy picture with my 35mm camera earlier, but I thought one thing I was going to say, it was really cool to see the sunspots on the image, which are blocked now still in the current one. Those sunspots were probably super Earth, mini Neptune sized spots moving across the star there. So that was pretty cool to see that.
Yeah, that was awesome. All right. Well, Doug, thank you for joining us.
Cheers,
Enjoy
thanks.
the rest of your weekend, and good luck with all of your research.
All right. Thanks.
And also, Doug, where can people follow you on social media? Because you are also actually active on social media.
I've been more on Mastodon lately, and DACMESS is my handle there.
Okay.
DACMESS.
Yeah. Don't ask.
All right. Well, we'll be chatting with you again soon, I'm sure. So
right.
thank you so much.
Cheers. Thanks.
All right. I think our Statue of Liberty has returned.
Oh, there we go.
Welcome back, Lauren. We can't hear you. You're muted.
Oh, I just did a whole bit for y'all, and I was
do it again.
I'm back again, about to drop a sick album about the solar
All right, never
eclipse.
mind. We can get rid of her.
Oh man, yeah. So I do have a much better connection now, and right now from here in Richfield, Utah, I'm seeing the end of the eclipse. Let me see if I can share my screen, see if it actually works this time.
Sounds like you took a screenshot.
Well, somebody had asked for a Statue of Liberty Lauren shot, so I had to.
There you go.
I had to jump on the opportunity. I'm sorry.
I thought that was Lauren trying to share her screen.
All right. Let's see.
There's a better shot of Lauren trying to be Statue of Liberty.
Okay.
Lauren, what's the temperature where you are right now?
I am satisfied.
It's actually pretty chilly, unfortunately. It's like, it was maybe 30, 40 degrees when I went out this morning. And it was actually getting a little bit difficult to work the telescope because my hands were frozen. So, there's always all sorts of things that come up.
We suffer
in
for the
these
art,
sorts of
right?
observation.
Suffer for the science.
Yes, we do. Exactly. I think, again, just because of the connection, I'm having trouble with the screen sharing again. But I can show you, if you can you see that? Can you see?
Let's give you a
there we
solo
go.
view.
Tilt tilt it down just a little bit.
Yeah.
Tilt it forward. There you go. There you go.
Yeah.
Tilt it forward.
Oh,
so you can
wow.
kind of
So
see the
you
very,
just
very
see.
edge of the sun.
Yeah. What
so
percentage
it's
do you think that
ending
is?
now.
Is it
I
like
think
5,
that it's
3?
about 3%. Yeah, 5 to 3%. That's what I was reading. In the in the sky is usually my go-to for these sorts of things. So the eclipse is about over here now. Everybody has kind of dispersed, which is why I can connect. It's because there's not as many people trying to, take pictures and stream it. But yeah, it's been really, really beautiful to watch, and it's going to be really cool to see that egress kind of happen, that, end of the moon transiting the sun. Just because it's such a neat thing to be able to watch an astronomical event in its entirety. It's not something that we get to witness all the time. So for one, that's why we're doing the live stream, but also to be out here in the field has been really, really cool, to see it start and see it end. I'll try to present one more time.
Yeah.
Nope.
How many
kind of happened today. That's okay.
So how many people have you had at your event there?
There were, when I pulled up, everybody was already in spots. There were probably 1,000 people, if not more, out here at Snow College, in Richfield, Utah. They were streaming. They were doing lots of cool stuff. Like I attempted to show you all the weather balloons, or the balloons that went up earlier. There were a couple that were grounded for a while. They finally went up toward annularity or afterwards. But yeah, the whole field was completely full. Lots of families out here getting their kids really interested in astronomy, which is always a really lovely thing to see. It's just really neat to see lots of people get together at these sorts of things and cheer at the sky. Yelling at the sky is one of my favorite things to do. So when other people yell at the sky, it brings me great joy. And I've actually made some friends being out here, people, wondering about the telescope, wanting to talk about astronomy. So it's been an overall really awesome experience.
That's great.
How many telescopes did you see out there?
Oh, probably maybe 50, I think. Most people came out with the eclipse glasses with a group of people. There were all different types as well, which is great. So of course I've got my Unistellar. See if I'm gonna attempt to do this. Can I show you there's the Unistellar. Yeah. So I've got my Unistellar out here, of course, and there were other different types of telescopes out here as well. And yeah, just cool to see different people's setups.
And did you by chance talk to anybody who was sending up the balloons and find out what any of the science they were trying to do was?
I did, but I was also trying to convince them to let me use their Wi-Fi. So
Fair.
So I was hyper focused. Yeah, it's been so interesting, and it's not, that the connection is poor. There's so many people trying to do a similar thing. But yeah, they were doing some really interesting science. I can't tell you what it was because I was trying to sweet talk them into using their Wi-Fi, which didn't work, but that's okay. Yeah, but it's really cool to see all the different types of activities that people plan around the eclipse. There were tents out here with different organizations, trying to get the word out about what they do, along with science experiments for kids. But kids using microscopes, so kind of going the opposite is the astronomy route. They were doing some cool science experiments there. So yeah, it was just like a really neat little festival. The whole town actually had a festival last night. It was a fall festival, but they were celebrating the eclipse as well. So just everybody getting really excited about this has been lovely. And in April, when we do this again, it's going to be even bigger.
Oh yeah.
Do you already have plans on where you're going to go for that?
Not yet. I know Michael Primm is already in a great place. for it. So maybe I'll
Yeah,
just go hang
it's
out
a
with Michael
party.
Primm.
It's a party at Michael
Come
Primm's
on,
house.
come
Is
on
what I've
down.
decided.
Party at
I have
Michael's,
I have another
absolutely.
friend I think who is I have another friend who's in Austin, and I've already told him that I'm like heading to his place and staying with him. So I'll be
Anybody
local.
look at the couch surf.
Yeah. Is it
The
pretty much
moon is
gone now,
just
Lauren? Do we have
like
just a little bit
Yep.
left?
It's just a
Oh,
really,
it's
really tiny sliver. I've got my, yep, you can kind of see it in the bottom corner. It's exiting.
Just barely.
It's
Yeah, the bottom
Yeah.
left.
Oh yeah,
transit,
just a
yeah.
little tiny,
Yep.
little tiny blip.
Yeah, I know, it's so cool.
Ooh, yeah,
See if
that's
we can
hard
get
to
a little
see.
bit of a better view. Yeah. It's like a really, really tiny sliver. There we go.
Oh, I guess.
Oh yeah, you can
back
just
up.
kind of see the
Yeah.
cutout, like
Yep.
just
Yep.
a little
Yeah.
bit.
Just a
It's
little
almost
dent-
enough
little
that
dent
I
there.
wouldn't be convinced.
Yeah. If you hadn't pointed it out, I'm not sure I would have noticed.
Well, that's
I
kind
would
of
have
the
said it
cool thing
was.
about these events is that, you know, you wouldn't know that this was
Mhm.
happening, especially if it was just a partial. I mean, you may not even know that it was happening. You may be going on around your, you know, daily life without knowing that this crazy, wonderful thing was happening. So that's why getting the word out about astronomy is so cool and important.
Mm-hmm.
Mm-hmm.
Lauren, you are doing the good work. Yes, you are.
You know what? I like to tell myself this. It's been an adventure. It has been an adventure. But yeah, I think it's done now. Where I'm at, we're back to just regular old sunlight. So this has been a really, really cool experience, and I'm super, super glad that other people got to share in the eclipse experience and share their screens and show everybody as well. And we have another chance in April, and of course there's other chances as well. I think there's a solar eclipse that will be visible from Europe and other places next year as well. I don't remember whether it was annular, total, partial, what be it, but there's always chances coming up. This just happened to be a really, really amazing one with a lot of people in the path.
Mm-hmm.
Yeah, and again, if you want to know when and where those are, timeanddate.com, just look for solar eclipses, and you can find when the next ones are, where they're going to be visible from, paths of totality, annularity, whatever. It's all there. It's an excellent website to go take a look at, and I highly recommend. All right. Well, we're kind of reaching the end of our it's done.
Totally done.
Yeah.
Totally done.
Lauren
here.
is Lauren is done, and she's finally got really good internet access. So of course.
Turns out it was the moon blocking the
yeah.
internet access as well this whole time.
And Michael's still got a decent chunk cut out here, so
Yeah.
he's still
You look
going
close,
pretty
you can
strong.
See it actually moving.
Yeah,
which I always
and there's
love.
you can see that top sunspot is now visible again. So
Well,
that's
that's what I love about the sunspots on there is the fact that it's a lot easier to see the movement when you have those spots on there. So
yeah, it gives you something to like anchor off of and notice how far away the moon is getting from it.
I just got a photo from Doug, so I'm gonna share it really quickly. One moment. If it downloaded, where did it's supposed to download? Grr. Okay, here we go. Let's see. So many buttons. Okay, so this is what Doug got at his one photograph.
Oh, wow.
Very nice.
So as you can see, we definitely have a lot of clouds here.
That's still though, that's a very nice shot.
It is a beautiful photo. So thank you to Doug for sharing that. That is beautiful. And like I said, a lot of the shots from the Bay Area are going to be pretty similar. That's what I've seen in my email for San Jose Astronomical Association, who, if they're still watching, hey everybody, sorry I couldn't be there. I was a little busy. But yeah, so it's been a fun time, and obviously I want to thank Lauren for helping organize so much of this. Thank you very much, Lauren, and for driving out to Utah. Thank you to my co-host Ryan. Ryan, you're a rock star. You're going to be doing stuff with me more often, I think.
Well, this has been great. Thank you, Beth, for hosting this.
And of course, thank you to Michael for having this amazing view that we've been able to share with you this whole time. I mean, 3 hours of just staring at that has been a joy, honestly.
Well, I'm just pleased to manage to mostly miss the trees. So,
and I saw earlier that you, or last night, I think you had done some calculations on how big things were and where you needed to point at. So, I'm really glad that,
a little bit. Yes.
Yeah. I'm really glad it worked out. And honestly, good decision on not driving. So.
Yeah, well, that, like I said, with what you guys were saying, particularly with what Lauren was experiencing, that wasn't even something I was thinking about. It's like, oh, yeah, I was just going to go to a park out by Fredericksberg. I'm sure it'll be fine, except for the fact that, well, if there's like 500 other people in the park,
everyone has the same idea.
Yeah. So yeah, I'll call that decision a success, and we'll move on from there, right?
Exactly. And of course, I want to thank all of the guests that we have had today. Dave Koster from Colorado Springs, Aparna coming in and talking to us from the Boerne Institute, Lucianne coming in and talking to us about habitability and astrobiology. And I've learned so much today. Mike Mitchell from Boerne, Texas, AstroAthens coming in to share her picture, and obviously go check out her social media. And Homera coming in from Tampa, Florida, with his beautiful view. And of course, last but not least, Doug Caldwell for coming in and talking about exoplanets and why transits are cool, and not just because of the ones we get to see like this. So, and finally, thank you to all of our viewers from around the world. I have seen locations coming in. I think it was pretty much every state in the United States, most of the provinces of Canada, and countries from Europe to South America to Asia. It was amazing, and I'm so glad that you all got to see this. And for those of you who were in the track of the eclipse itself, I hope you got to go out and look up safely with glasses, or a chance to make a little pinhole viewer, whichever way.
Colander.
A colander. I'm still going to go with the colander. It's so much fun. And just remember to clean it out
first. That's a guerrilla astronomy going on there.
Yeah. Just remember to clean the colander out before you use it. And we'll be hopefully back in April with some more live streaming, and we will be back this next week to talk about the Psyche mission. Franck is going to be talking to someone from that mission, which just successfully launched on yesterday. On Friday the 13th of all days. So yay. So join us all back then. Don't forget to do the things of liking, subscribing, sharing, commenting, all of these. And we appreciate all of you here. So thank you so much, everybody. And we'll see you next time on SETI Live.
Bye.
Bye, everyone.
Everybody next time.